Thank you, Anna-Rita, for the kind introduction. Yes, Austria Tech was the coordinator of the INFRAMIX project, or still is, because it's up to end. INFRAMIX is about the preparation, so to say, for the road infrastructure of the future in a very dynamic environment. So more the coordination and communication parts for the future of automated driving. A lot of other international projects are going on in the field. Many platforms are working on that. And what we see also with today's event is exchange with others and initiatives on a global scale is key in this very specific topic. So INFRAMIX is trying to bring, so to say, transparency and insights and evidence towards a safe mix instead of a mess in traffic flows of the future. So it's not only about what for, but how to evaluate the impacts. In the beginning of the project, we honestly have to say our perspective, and I think the perspectives from many of us a couple of years ago have been quite optimistic on how fast we move forward towards level 3, level 4 vehicles or connectivity functions. And it was a real challenge for the project to come from general simulation tools towards the analysis of a specific support in a specific scenario or situation. So this shaping of, let's say, the competencies and how we are got to be able to analyze exactly what the vehicle needs in which kind of situation and what infra could provide and how, I think this was key, and we have made really, really good progress in the project. One of the outcomes, the ISAT levels, so the infrastructure support levels for automated driving, I think this is a key result for a future, at least theoretical infrastructure classification we should work along. Let me thank all the partners and the project teams. Above all, of course, the coordinator on behalf of Austria Tech, Martin Dierenberger. He will be also with you the whole day today and also giving you the highlights of the project. Many thanks to our technical coordinator, ICCS, and really many thanks for the partners, but also the surroundings for working together in a really outstanding European project. I wish you all a successful and inspiring final event. So let this be an inspiration for the shaping of a common perspective towards the continuation of this good and hard work we have done so far. So enjoy the day and thanks a lot. Anna-Rita.
Here I am. Thank you, Martin.
Good.
Thank you for your introduction and presentation. I would like right now to introduce our coordinator, Martin Dierenberger. He's senior expert at Austria Tech. Martin, are you here? The floor is yours.
Yes, I'm here. So thank you very much. I will now share my screen and in the first give you an overview on INFRAMIX, on what was our idea, what was our starting point, and as well I would like to give you an indication on the highlights we had in the project. So I hope you can see my screen now.
I can see your screen all right.
Okay, perfect. Thank you very much. Okay, what was our starting point in the INFRAMIX project? Or let's say, I would like to give you first, very briefly, the project facts. INFRAMIX was a project running for 3 years, and it's coming to an end in the next days. It was funded by the European Commission with about 5 million euro, and we are a consortium of 11 partners throughout Europe, representing different stakeholder groups in the area of automated driving. So it's ICCS, ASFINAG, Fraunhofer Focus, Siemens Mobility, Virtual Vehicle, autopistas, ENIDE, the Technical University of Crete, TomTom, BMW, and Austriatech. So what was our starting point for INFRAMIX? So I think we can say that mixed traffic situations will increase in future. So this is quite sure. And already now there are several vehicles on the road which have in some way automated functions.
Martin, I'm sorry to interrupt you. I can see your presentation mode, just for you to know.
Okay, thank you very much, Anna-Rita. Try to, just one moment. I'm sorry for that. We tested this. Does it work now?
Just like before.
It's like before.
Okay, better now.
Now it's better.
Yes, thank you.
Okay, so I apologize for this, and yeah, I come back to our starting position. So mixed traffic situations will increase, and we also expect, at least in the beginning of this phase where we have automated and non-automated vehicle on the roads, that efficiency and safety will decrease. There are already some results from other projects which have investigated this. And I think it's also kind of obvious since there are new ways of interactions between human beings and machines, the vehicles. Also, the vehicles are of, I would say, different they have different functionalities and so on. So I think this will decrease efficiency and safety. And we think that the infrastructure of support can increase efficiency and safety, and therefore solve a lot of problems which arise due to these mixed traffic situations. We will have, so in INFRAMIX, we looked into different levels of support which we could provide to vehicles. So one level is to support the perception capability of automated vehicles, for example, by informing the vehicles on incidents on the road ahead, also on roadwork zones, for example, including a different lane layout. So this is a direct support of vehicles. Then, on another direction, we support with our INFRAMIX measures. We provide better conditions for maneuvers for vehicles. So, for example, if we are in a bottleneck situation or near an on-ramp, we give an advice to those vehicles which are on the main road to change lane to the left so that there is more space available for the vehicles which want to enter the highway and make so the maneuvers easier. Another kind of support we give is to the drivers of conventional vehicles. So we investigated how we have to communicate with drivers of conventional vehicles, which signs we are needed, and we developed a new physical sign also for AD lanes. And finally, we of course tried to improve the traffic situation in mixed traffic environments. So in order to increase the efficiency in bottlenecks, we developed, for example, a get advice controller. So this was have been some levels on a more or less general level, but of course we need to apply our measures to very concrete situations. And to be able to do this, we have selected in the INFRAMIX project 3 scenarios, and these scenarios we have investigated in detail. So there was, the first scenario was the assignment of dynamic lanes to automated vehicles depending on the percentage of automated vehicles in the traffic. As a second scenario, we investigated roadwork zone, which can be a very problematic area, and it's therefore really important to look into this. And as a third scenario, we investigated bottlenecks. Our focus in the INFRAMIX project was the highway environment, but of course, in some way measures can be transferred to other situations and other roads as well. So finally, I would like to give you an overview on our approach in INFRAMIX and also what have been our building blocks. So on the one hand, we have developed solutions. Then of course, if we develop solution, we have to evaluate this in order to know if they work, if we are successful with them. And based on these evaluations and our learnings in implementation of solutions, we provided recommendations. So related to solutions, we have developed traffic control strategies as well as estimation algorithms for mixed traffic environments. We have developed and implemented the elements needed on the digital infrastructure side, but also on physical infrastructure elements. In order to be able to evaluate all these things, we needed, of course, to rely also on simulation because there are not so many automated vehicles around right now. And therefore we had a strong simulation focus and have developed simulation tools on the microscopic level, but also on the submicroscopic level, where we investigated the behavior of automated vehicles on a very detailed level. We have implemented the elements in the real world, and we made a combination of real world and simulation, which we called hybrid testing. So these are our simulation tools. And then out of this, we have elaborated several different ways of recommendations. So we have developed this infrastructure classification scheme, which was already mentioned and which has been since then discussed also in many other groups. We have looked into safety parameters. We have developed a roadmap and exploitation plans. And so what you see here, these are, so to say, the elements of the INFRAMIX project. And on most of the elements, you will get a very detailed insights in the coming hours. Since we have promising results received for a lot of the things we have investigated, I would also take them as the highlights of the project. Yeah, and now I will hand over back to the moderator, and I hope that you enjoy our final conference. Thank you.
Thank you so much, Martin. Thank you for your presentation. I will now pass on the floor to Daniel Turton. He's senior expert at Siemens Mobility. So Daniel, whenever you're ready, we're waiting for you.
So hello, everybody. My name is Daniel Tötzl. I'm working for the ITS department at Siemens Mobility Austria. And today I would like to introduce you to our findings of the digital and physical infrastructure in INFRAMIX. So please let me switch to show my screen. So Can you already see my screen, Anna-Rita?
I can see your screen, all right. I can't see your presentation yet.
Okay, then it's the wrong screen. I'm sorry for that. So, Anna-Rita, please can you confirm that it
Yes,
works?
I confirm that I see your screen and presentation. Okay, go
Thank
on.
you.
Thank you.
So let's start with my presentation. At first, I would like to start by looking at our INFRAMIX objectives and our initial situation for the real environment implementation. For this, it is based on three major topics: the design, the development, and the linking of infrastructure elements, the integration of traffic management functionalities, and last but not least, the communication between the infrastructure and the end users. So in consideration of the design and the development of the infrastructure element, the development of the architecture for INFRAMIX required to cover the interaction of all stakeholders which are involved for supporting conventional as well as connected automated vehicles. Therefore, it was necessary to consider already existing infrastructure systems as well as further enhancements which gets combined with each other. The combination of physical and digital infrastructure elements was so a major goal in order to connect all involved stakeholders. A further goal of INFRAMIX was the requirement of implementing traffic management functionalities to the architecture, which deals with the future rising coexistence of the mixed traffic. So these traffic control strategies requires a continuous input of traffic data measurements, but they also require data interfaces in order to trigger its results to all types of vehicles. And this leads to our third major objectives of the INFRAMIX real implementation, the communication to the end users. So therefore, it is required to implement functionalities to be able to inform conventional vehicles, and at the same time, it was required to implement functionalities to inform connected automated vehicles by applying new digital communication technologies. So therefore, we had to analyze on the one hand visual needs and gaps for conventional vehicles, and at the same time, we had to define a way how we are able to implement the digital end user communication by applying communication technologies. So therefore, we decided and considered the implementation of a hybrid digital communication exchange, which enables, on the one hand, the communication via cellular link, as well as the communication via ITS-G5. On the next slide, you can see our resulting INFRAMIX architecture based on these objectives and based on our initial situation. And this architecture covers the requirements and needs. So this is the high-level architecture of INFRAMIX, and this concept includes the integration of various stakeholders which all support the future arising traffic in a combined way. The architecture itself of INFRAMIX is based on the road operator's traffic management, including an INFRAMIX-related enhancement, which we consider as the INFRAMIX Management Center. This management center forms the core element of the INFRAMIX system architecture and includes functionalities for traffic control strategies, as well as the distribution of resulting traffic commands to other systems of the architecture. The INFRAMIX Management Center also is considered as the central source of information, which collects available input data, which runs the traffic control strategies, and which triggers its distribution to all stakeholders. The IMC is therefore acting as a distribution hub to both communication paths, having on the one hand variable message signs for drivers of conventional vehicles operated by the road operator, and as well the already mentioned hybrid digital communication by having a cellular link as well a cellular link operated by the traffic service provider as well as the original equipment manufacturer, and further also the ITSG5 link, which is operated by the road operator. Both digital channels are responsible for the distribution of digital messages to connected automated vehicles, and these messages include the information about resulting traffic rules or recommendations. So based on this high-level architecture, we were so able to form an INFRAMIX end-to-end process, which is set up on a repetitive three-step approach. This three-step approach is divided in following three steps. At first, the data provision. So the first step is the provision of traffic data by all involved stakeholders to the INFRAMIX management center. So this is the input of traffic data measurements. This forms the major requirement in order to run the the traffic management functionalities. And these data is provided on the one hand from the road operator itself, but also from linked traffic service provider and OEMs. The second step sets up on these provided input data, and therefore the INFRAMIX Management Center evaluates and processes these data in order to run the implemented traffic control and estimation algorithms. And as a result, reliable rules and recommendations are going to get developed in dependency of the current traffic situation. And the result of these control strategies further leads to the third and last step of this repetitive approach, which means the distribution of the information. So therefore, the INFRAMIX Management Center triggers the distribution of the resulting rules and recommendations to all communication paths, having on the one hand the visual message signs, but on the other hand the hybrid digital communication technologies. In the following slides, I will get a little bit deeper in these three steps, starting, of course, with the first step of the data provision. So the data provision to the INFRAMIX Management Center uses its high advantage of having different stakeholders involved, which are all able to provide traffic data. So this consists of the provision of aggregated traffic data, for example, information of average speed, minimum and maximum speed, as well as the traffic volume of a predefined detection zone. And the provision of the aggregated data can thereby be realized by physical sensors of the road operator itself, but also by the connected digital communication channels, having on the one hand aggregated traffic data provided from the cellular service provider, but also on the other hand the input of aggregated data from ITSG5 roadset units, which receives and aggregates so-called cooperative awareness messages, which are sent out from passing CITS ITSG5 equipped vehicles. Additionally, the INFRAMIX system architecture foresees the provision of single vehicle data, which is provided directly by linked OEM vehicle services. Of course, the provision of input data requires further communication interfaces, and this was part of our project, and therefore we specified different communication interfaces between all responsible entities, having communication from the Traffic Management Center to the IMC, but also from both digital channels. The second step of the end-to-end process is formed by applying the traffic control and estimation strategies. So these algorithms are considered as a major aspect of the INFRAMIX Management Center, and this creates the opportunity to optimize an overall traffic efficiency of the entire road infrastructure. By the implementation of such traffic state estimation and control strategies, the IMC is going to get provided with traffic management capabilities in order to address new traffic control strategies in order to execute, for example, dynamic lane assignments, but also time cap advices, variable speed limits, or lane change advices. Of course, also these control strategies requires the variant of traffic measurement data, which is provided as at the first step, which I already announced. There will be a dedicated slot further on about control strategies, so I will not get in detail right here. And last but not least, the third step of INFRAMIX, of the INFRAMIX end-to-end process, is the distribution of the resulting traffic rules and recommendations to the end users. So as already announced, we have to deal with both kind of types of vehicles, having on the one hand the conventional vehicles by using variable message signs, but also having future connected excuse me, please could you mute yourself? But also having digital communication channels, which provides a connectivity to future connected automated vehicles. The digital hybrid communication approach is formed on the one hand by the wide range cellular communication and as well as by the ITSG5 short range communication link. So in INFRAMIX, the cellular communication channel is implemented by the cellular service provider and the OEM vehicle services. So therefore, there's a link between the INFRAMIX Management Center and the cellular service provider in order to transmit resulting control commands. And the service provider is so able to process these received control commands and is also able to forward them subsequently to its connected cellular end devices like smartphones, but also to further distribute it to connected vehicle backend services so that they can distribute the information to its connected vehicles. The second type is the already mentioned ITSG5 Airlink. This is a Wi-Fi based communication technology which is realized for the infrastructure to vehicle communication by roadside units which are equipped along the highway and which are directly connected to the IMC. The RSUs broadcasts therefore the control commands received from the IMC by applying standardized CITS messages to local passing ITSG5 equipped vehicles. And therefore, for the ITSG5 approach in INFRAMIX, we used on the one hand already available ITSG5 Day 1 messages, but what was also very special for INFRAMIX, we used for the first time new Day 2 message extensions, which are already currently in standardization process, like the IVI message in version 2. Further, the system architecture, of course, includes the connection to the variable message signs, so to be able to spread the same information to conventional vehicles. Therefore, we applied most for the use cases of INFRAMIX, most already existing variable message signs were able to use. Nevertheless, one message sign which Martin already mentioned was needed in order to tell conventional vehicles about the dedicated lane assignment, and this is the one which I put here on the slide, displaying a vehicle which is connected, and this means that if this is operated, that there is a dedicated lane. We also did a demonstration test with these signs in Girona in Spain last September. So coming to an end of my presentation, in conclusion, the INFRAMIX end-to-end solution underlines the combined effect of different stakeholders in support to support the future arising coexistence of conventional as well as connected automated vehicles. The system architecture reveals the necessity of having one central source which is responsible for running a traffic management. This means having one central infrastructure element which has a complete overview of the current road situation and which is able to run control mechanisms in order to support the mixed traffic. And last but not least, INFRAMIX also illustrates positive effects of applying digital hybrid communication approach by having, on the one hand, the possibility to support vehicles equipped with different technologies, communication technologies, but also on the other hand, the opportunity to increase the input data for running a traffic management. Thank you everybody for your attention. I think we might have some time left for a short Q&A session.
Yes, so thank you very much, Daniel. So before I start asking questions, I just would like to say, since this question has been raised for several times in the question box, that we will provide the presentations afterwards, so we make them available. So one question I would like to ask Daniel is, what are the most important or the highest challenges from the implementation part of view concerning these mixed traffic situations, and yeah, what would be the most important next steps?
So first of all, I think it was quite important and quite challenging to find a way how to distribute information to different channels. There are already existing digital messages which are defined for ITSG5 communication, but we also had to define a way how can we transmit the same information to other channels, to the cellular service. And at the same time, we also had to consider how are we able to apply the results of the controls strategies to conventional vehicles. So this was one of the most challenging implementation topics, to find a common way which is not just be able to get used for our INFRAMIX project, but also which can get applied in the future in general. The next steps, of course, is to agree using such protocols, but also what was especially not in the real test environment was also the focus on how can we ensure the security of such digital communication. Of course, there are already existing parts like PKI, a dedicated PKI, but this was something which we, of course, think about, but it was not in scope of the real demonstration. So this is definitely one of the next steps which has to be done.
Okay, thank you very much for the answer. So I would like now to give back to Anna-Rita and for the next presentation.
Okay, very well. Thank you so much for your presentation. Now I would like to introduce Panagiotis Litridis. He's senior researcher at ICCS, and he will start the presentation on ISAT classes. Then I will be happy to introduce Yannick as well, that will conclude this same presentation on ISAT classes. Hello, Panagiotis. The floor is yours.
Hello. Hello. Thank you, Anna-Rita. So I would like to welcome you. Good morning also from my side. I'm the Technical and Innovation Manager of the INFRAMIX project. I'm going to discuss today about the ISAT classes. What I would like to mention before is that we had a lot of activities during those 3 years, so I'm happy that we have so many attendees today that they can follow our developments, let's say. Just a few words about myself. I'm a senior researcher at ICCS, and I'm involved in the ITS field the last 14 years. So a lot of, let's say, years in the field. So let me share my presentation. So I think you can see it right now. Okay. So I'm going to discuss about the ISAT classes I mentioned before. The outline of my presentation is about motivation, the background behind this work, let's say, the methodology, an overview of the ISAD classes, while my colleague Yannick Wimmer from Aspen will follow with some more details on those classes and with detailed examples. And then I will conclude my presentation. I will highlight some next steps in the field of the ISAD, let's say, classification. And in the end, I will have some sources of information for the interested people if they would like to spend some more time on the ISAD classification scheme. So a few words about the motivation behind this work. In the last years, let's say 10, 15 years, we have heard a lot about the advanced driver assistance systems, the evolution to automated driving functions. A lot of the research activities were focused on the vehicle side, so very vehicle-centric. So we have heard a lot about taxonomy, different taxonomies of the AD functions in the last years. The most prevalent one right now is the SAE levels of automated driving that you can see on the left, on the right side of the screen. So thinking about that, we said, okay, we have to do something also with infrastructure side. This was started, let's say, a bit recently with also with the European Union, the funding in this direction. So if I'm not mistaken, the first projects that were funded in order to take into account the infrastructure side was around 3 years ago, INFRAMIX Coexistence and Translate. So right now we have a lot of activities around infrastructure and how the infrastructure can support automated driving. First of all, it's really important, the role of infrastructure in transition period, where we have mixed traffic. We have conventional cars, connected cars, automated cars. So we need to support them in order to avoid degradation of the traffic efficiency or not to have any issues with traffic safety. Through the infrastructure, we can enhance the electronic horizon of all the connected vehicles in the ecosystem. We can also facilitate, because the vehicles should drive on the same road, we could facilitate through this infrastructure the cooperation between the different types of vehicles with the different capabilities and the different automation levels. As I mentioned before, we can manage and guide the traffic in a way that we can avoid potential bottlenecks or critical situations. And also what is really important here is to highlight the fact that we need to have consistent, let's say, physical and digital world. So whatever we transmit through the signals, as Daniel mentioned before, we need to have the same representation for the conventional cars in the physical infrastructure. And all those things, and especially motivated by the SAE levels for automated driving, we said it's important to classify also the infrastructure. That's why we have this kind of taxonomy I'm going to discuss with you today, the ISAD classes. So a few words about the methodology we followed during this work. Let's say we created the architecture Daniel shared with you earlier. So we had the definition of the different systems, the main components, and also the associated challenges for deployment. Then we tried to group the state-of-the-art activities in 3 different layers: the physical, digital, and operational layer. I will spend a few minutes in the next slide to explain what we mean by that, physical, digital, and operational. Then we try to categorize the different information coming from the infrastructure and also identify the means that we're going to communicate this to the vehicles, if this is ITS-defined, if this is cellular, if this is visual, let's say, signs, VMSs, and so on. And the result was to create a classification scheme that, as I can, let's say, as we say, it's a gradual enhanced scheme. It's an incremental scheme where each class includes the features of the previous class. So it builds on top of the previous classes. You will see in the next slides, let's say. And this is a continuous work. We are trying to continuously improve this classification scheme. You can see what are the next steps that we are planning in the end of my presentation. But we had continuous consultation with experts, with the INFRAMIX advisory group, through the workshops in order to, let's say, improve this classification scheme. So the road infrastructure, as I mentioned before, can be classified into 3 different layers: the physical layer, the digital layer, and the operational layer. Just for you to understand, the physical layer is the physical world we have outside, the road signs, the road markings. all the equipment we need to communicate with a vehicle. So it's the physical world, let's say. On the other hand side, we have the digital part, the digital representation of this physical world. So we have mainly the high definition maps, we have the communication technologies, the signals, and so on. And last but not least, we have also the operational part, which is very important because it's, as the name implies, the operational aspect of this, of the infrastructure. So we are talking about traffic management, traffic control strategies. So it's really important. So going to the most important part of the presentation, it's the classification scheme. So we have identified 5 different classes, starting from class E, which is the typical conventional level, towards class A, which is the most advanced. As you can see in this table, on the right side of the table, we have columns indicating the different digital information we're providing to the AVs. So starting from the, let's say, conventional class, which is class E, you can see here we have just what the road infrastructure is supposed to have today. So clear lane markings, well-maintained roads, clear road signs, and then the rest is up to the software of the AV, the automated vehicle, to recognize the signs, the road geometry, and so on. So we don't have any kind of digital support. Then if we go to class D, we are starting to have some static digital information, just some information about the static road signs, the maps, and nothing more. So we are talking about some minimum information from the digital world. Then going upper to class C, we have all the information that we have in the infrastructure, static and dynamic, are available in a digital format and can be provided to the AVs. So information from the variable message signs, warnings, incidents, weather notifications, and so on are included in this class and can be transmitted directly to the connected vehicles. Then going to class B, we have an infrastructure which is more advanced. It can support higher levels of automated driving. It can perceive microscopic traffic situations and provide more data to the AVs in real time. For example, traffic congestion, it is automatically recognized and transmitted to the vehicles. And then we have the highest level, which is class A. We name it cooperative driving because based on real-time information of the vehicles which are on the road, of the infrastructure capabilities, we can go one layer up and we can guide those kind of automated vehicles in order to optimize overall the traffic flow. So we can have we can send them speed advice, time gap advice, and lane advice. So this is the most advanced, let's say, layer. More information will follow in the present. I would like right now to let's say launch a poll. So I would like you can please vote how you rate the ISAT classification scheme that I was presenting. If there's a glitch with the software, so please be in full screen mode if you like to vote. This is an issue with the tool that we realized during the rehearsal. I can wait for, let's say, 10 more seconds. I think people are voting. So you have 5 more, let's say, seconds to vote.
Panagiotis, I'm sorry to interrupt you. Just let me say that some people might experience some issues with full screen mode or Windows mode. So try to switch among the two so to have a better view of this poll. Thank you.
Okay, thank you, Anna-Rita. So I think most of the people have already voted, so I can close the poll and I can share the results with you. So I'm thankful that most of you have voted that it's very useful and useful. So it seems that we have, let's say, you agree with our activity, that we think ISAT is a very important, let's say, tool that we can use in the future for automated driving. Of course, some of you are not yet familiar with this. So we have a percentage of 16% of undecided. So I hope this 16% will go to useful or very useful when we end this presentation, and also Yannick's presentation. So let me go forward, close this, hide the poll, and continue with the presentation. So conclusions and next steps. First of all, the work we have done so far is a work that we need to use in order to guide the investments in the future and target them in the road infrastructure in order to upgrade the level. So if someone wants to go, a road operator wants to go from class D to class C, through this infrastructure classification scheme, he can see what is necessary. The work we have done so far is mainly focused on highways because of the also consortium synthesis that we have to highway operators and the scenarios we have, but this could be really easily extended to urban and rural roads. With respect to the future direction, we would like to see also the dynamic aspect of this classification scheme. So we are not interested just to statically classify some roads and mention this as this is class A or class B or class C, but we would like to see, in case of an event, of a disruption, of a let's say problem in the traffic management center, that we can let's say if we degrade that that level in a dynamic way, or in case we have snow or other incidents on the road, automatically the level of the infrastructure should be degraded. And also, what is very important, future direction, is to investigate how we can support the operation design domain, how to close the gaps in the field of ODD. Yannick will say more about that just right after my presentation, but also we have a very nice presentation with respect to ODD and ISAT by Tom Malkin from the Commission towards the end of today's workshop. So for the interested, let's say, readers, some more information about the ISAT classification can be found in the book chapter that was recently, let's say, published in the Cooperative Intelligent Transportation Systems book that was published in 2019. It's chapter 14. And also you can find more information on the public deliverable that we have on classification scheme in our website in INFRAMIX. So you will receive the presentations at the end, so you can have also this information. Thank you very much for your attention. So I'm open to questions.
Thank you, Panagiotis. If you're right with that, I will leave now the floor to Yannick, and then I would rather leave all the questions to the end of this joint session. So
this
Yannick,
is fine. Okay.
Okay, thank you so much. Yannick, if you're ready, the floor is yours. Please, everybody be reminded that we invite you to submit your questions through the question box on your right. Please do not raise your hand because we won't have time to leave you the microphone and listen to your question. Thank you.
Hi, my
Yannick,
name is Yannick.
Okay,
Wimmer.
good.
Yeah.
Yes,
Okay.
now I can hear you.
Yeah. From ASFINAG. ASFINAG is the Austrian road operator, and I'm also working in a field of connected, cooperative, and automated driving. And I'm struggling to share the right screen. Anarita, can you tell me? So because I have the wrong screens shared at the moment, or otherwise I could just shift it over there, but.
I'm not sure you're sharing the wrong screen. I can see that.
Oh, I know I am sharing the wrong screen because you should be seeing this.
Okay.
Yeah.
Now
Actually,
I can see your screen.
Okay, then let's do it like this. Let's see. Okay. So, okay, but then
You're
again.
in presentation mode.
Then again, I'm in presentation mode. That's what I was thinking about. That's the problem. Okay, just give me. Yeah. Because, and I'm definitely not in presentation mode if I could share the other screen. Does somebody have a tip for me how this could work? It worked in rehearsal, but there it is. I think I found it.
Now, okay.
Yes.
Everything's
Okay.
fine.
Sorry about that. Yeah. Okay. Yeah. But now everything is fine, I guess, right? Yeah.
Good. Yes.
Yeah. Okay. So thanks, Panagiotis. I will follow up on what Panagiotis said with some classes with the view of an infrastructure operator, of a road operator on this ISAT topic. So first of all, where does it come from? Where did this idea come from? Well, vehicles have something called an operational design domain. So a domain in which they can be more or less guaranteed to work and just keep search. This very nice example. I like the drawings of Tom Alkim, by the way. So we will have a keynote of Tom Alkim later on. And he drew an example here where you could imagine, okay, you're driving on the highway. So on the first mile, you're not on the highway. Then from here to here, from B to E, you're on the highway. But on the highway, there can be some things that that come into your way of the operational design domain. So there could be a different road layout, there could be some congestion, some adverse weather, and this would lead to well, that you have to take back control of the automated vehicle. And this is something that, of course, obviously we want to avoid. Also, the OEMs want to avoid, and their infrastructure comes into play. And so what you see here is the equipment that we as ASFINAG have on our test track around Graz. So this is maybe not representative for our network, but rather it is one of the best equipped road strips in Europe, or maybe even in the world, if one can say so, because we have here, well, things like dynamic displays, weather stations, traffic detectors, cameras, but also radar sensors. This might be the most advanced things. And we also, and this is something that we addressed in INFRAMIX a lot, we have CITS roadside units for providing the digital communication, the ITS-G5 communication, but also a data interface for providing this via the cellular way. And yeah, the question about ISAT was, okay, and how can you somehow categorize this so that people know what you're talking about when you say what kind of infrastructure do you have on the road? And I will give you just a slightly different angle than Panagiotis on this one, because we as an infrastructure provider, we said, okay, maybe let's have a look. So what does this mean from the infrastructure side, and what does it mean from the automated vehicle side? So let's construct this from bottom to top, maybe. So if you have basically not really any automated vehicle support from the infrastructure side, then an automated vehicle would have to recognize everything by itself, right? The road signs, road geometry. But actually, most of the roads that we have nowadays, actually, they have at least some static digital information. They have a map, and still on such a map, then is still, if you only have the map, then some dynamic things like traffic lights or short-term roadworks warning or whatever. Dynamic road signs would have to be recognized again by the vehicles itself, but at least you would have a map support. And then further on, it would go to dynamic digital information. And here, this is where infrastructure really comes into play. Then this is when we as an infrastructure would provide already dynamic information. And of course, the automated vehicles would need to perceive this information. And moving on, and then at some B, it would even be, so then we should be able to even provide some microscopic traffic information. And for the AVs, the main part is it should be in real time then. So you would really receive some traffic information in real time. This is basically CATS day 1. This is, for example, a roadworks warning. So a roadworks warning would reach you in real time and would be displayed here on the screen. And yeah, this would also already be ISAT B. ISAT A, then okay, this is something that's in the future still, and it's not so much defined at the moment because it's really, so we're talking about CITS day 2 or even day 2 plus services here. So we're thinking about something like platooning support or some collective perception, something like this. Yeah, so this is still to be defined a bit in the future also. So maybe that you don't get the wrong impression here. This ISAT classification is not yet written in stone. This is a proposal from the INFRAMIX project that really hit a nerve on the European level, but it is something that is still in discussion, and it's a good basis for a discussion, but it's not written in stone so far. Okay, due to the running time, I will skip this slide here. Basically, I've said everything, and it's just some more examples of some CITS use cases. I have a short poll just before the end for you. Just trying to start it. It is this one. No. Yeah, this one. So I would be interested in what class do you think that the majority of your national highways belong to? This could be different in different countries, although I don't really think so at the moment. But and it's so you can't do anything wrong here. It's just what you think that the most highways belong to. Okay, I see you are voting. Great. Maybe let's give you another 5 seconds, but I think voting is done. There are no more changes in here. Okay, so I will close it. And let's have a look. So the majority of you voted class D, and then, well, it's spread out over a lot of different, more or less equally spread. So the majority, at least as far as Austria is concerned, the majority of you is right. Okay, I think. Okay, yep. As far as Austria is concerned, the majority of you is perfectly right. Of course, we have some hotspots in Austria where we already are testing some additional stuff, and they are marked. For example, here the green one, the ISAT Class B. This would be the test track around Graz, but the majority is still Class D in Austria, where we have maps, even HD maps, but we do not yet provide some dynamic information. But this will soon change when we at ASFINAG will be providing, so we will roll out some CITS technology in the coming years, but I will talk about this in the afternoon. So yeah, that's so much from my side.
Okay, thank you very much, Panagiotis and Yannick. Since we are already a little bit over time, I will ask you one question, and I would let it open to you who would like to answer it. The question is, how is the ISAT classification related to semantics of autonomous vehicles?
So maybe I can give a first answer. So so far we have done an exercise how to map, let's say, the ISAT classes with the automation level. So it's something similar. It was an easy exercise, and it includes a lot of parameters, because to classify already automated functions to the different levels is really tough work that has been carried out in several European projects, from Adaptive, L3 Pilot, and other projects. So its taxonomy and classification is a challenge task. If you would like also to combine them, classifying the infrastructure with capabilities of the vehicles, it becomes a little bit difficult. So we have started this exercise. So we are not going to conclude it in INFRAMIX, but as Yannick mentioned, this has gained momentum in several fora. So we believe ISAT classes will continue evolving through ODDs, through this kind of automated vehicles capabilities and so on. So this would be my short answer.
Also, if I might jump in, or maybe some organizatoric thing, some of you might be seeing a black screen right now. This is also the full screen issue. So in full screen, you might be seeing a black screen in transition, and also you are not able to vote in the polls. So maybe it's better to view the webinar in window mode, at least for this. Okay, and so I'm not quite sure if this question targeted also the interlink between the SAE levels that I think are, at least I understood this question in this way, the SAE levels for automated driving, which are characterizing the vehicle capabilities, and well, ISAT is in the infrastructure side, and so at least I'm asked. So people ask this a lot. So to me, this is something independent, more or less, because well, just think of it like this. Also, a highly automated vehicle would need to be able to drive also on roads that have ISAT E. But, and here where ISAT comes into play, ISAT could help to close those ODD gaps, that operational design domain gaps that I was starting my presentation with. So it is something that can support. The S in ISAT stands for support. But to me, this is something that stands in parallel.
Well, thank you very much, Panagiotis and Yannick. Very interesting presentation. And now I would like to leave the floor to Ioannis Papamichail. He's associate professor at Technical University of Crete. Here's Ioannis. Hello,
Hi,
Ioannis.
Narita.
The floor is yours.
Thank you. Thank you for this introduction. Good morning to everyone. And at this point, I have to share my screen. Can you see the presentation now?
Yes, now I can see the presentation in full screen mode. Although I can also see the your GoToWebinar panel on your right. That's just a black box. So
Okay,
be aware of that.
I cannot remove that.
No,
So,
yeah.
okay, of course, the development and the evaluation, part of the evaluation that I will present today of the traffic estimation and control strategies has been performed by a group of people. Here, the Dynamic Systems and Simulation Laboratory of the Technical University of Crete. The group is led by Professor Papageorgiou and includes myself and some colleagues that also performed evaluations, Mr. Margondonakis and Ms. Doko. As said, we have developed a traffic state estimation and traffic control algorithms, and we will have the chance to enumerate these strategies also in the following slides. At this point, I would like to emphasize that software tools and interfaces have been developed for use within the co-simulation environment and the IMC, the INFRAMIX Management Center that was presented already by Daniel. The co-simulation environment will be presented next by our colleagues from Fraunhofer Focus. So in conventional traffic, real-time traffic data are provided by spot sensors positioned at appropriate locations. However, we are now looking at an environment that includes connected vehicles. Connected vehicles may communicate their position, speed, and other relevant information, which means that they can act as mobile sensors. And this allows for a sensible reduction and potentially even elimination of the necessary number of spot sensors, which would lead, of course, to a sensible reduction of the purchase, installation, and maintenance costs for traffic monitoring. Developments considered both the aggregated case, the cross-lane case as we call it, and the case of lane-based estimation. The latter is essential for some control applications. Information is provided by connected vehicles, and it is fused with measurements stemming from a minimum number of spot sensor measurements that are necessary, of course, for flow observability. Lane change information from connected vehicles has been exploited to assess the level of lateral flows. This is a piece of information necessary for lane-based estimation. And finally, robust and practice-relevant Kalman filter-based tools have been developed. So we will start with some results for the cross-lane case, the estimation for the cross-lane case. Our goal here is to estimate the mainstream density and the ramp flows. As currently the penetration rate of connected vehicles remains at low levels, and on the top we are not really sure about the actual numbers in the field, we performed evaluation of the estimation tools using data from the simulations. So we know the ground truth and we can compare that with the estimates. So for the network, which will be presented in detail in the next presentation, we run sets of 10 replications, starting with different seeds affecting any randomly generated values in the simulation. And we do that for different penetration rates of connected conventional and connected automated vehicles. Just some information about the magnitude of the problem. The stretch that we are looking at is a 4-lane motorway of some 19 kilometers that includes 3 on-ramps and 2 off-ramps. Here we present some plots that include average values over all replications for the coefficient of variation, which is a performance index that shows how close we are to the real values. The plot on the left presents the coefficient of variation over different penetration rates for the case of density on the mainstream, while the plot on the right presents the corresponding information for the case of ramp flows. We can see that there is just a small deterioration of performance when we look at lower penetration rates. So if we observe now the real and estimated density heat plots over the whole stretch for the whole simulation period of 3 hours, we cannot really say the differences. This is the case for a pretty high penetration rate of connected vehicles, 70% in this case. And I picked up this case as the high penetration rate of AVs creates some more congestion, which is a very challenging problem for the estimators. The estimations are similarly good, though, for lower penetration rates as well. But let's now have a look at the segment where congestion is first created. It is a merge area with an on-ramp. On the right plot, we can see the real and the estimated density trajectories. The real one is the blue curve, while the estimated one is the black curve. I think that we can all agree that the estimation is very good. On the left plot, we can see the real and the estimated flow trajectories for the same segment. And the estimation, again, for the flow, this time is similarly very good. Let's have a look now at the estimated flows for an on-ramp on the left and an off-ramp on the right. Apart from a very short warm-up period, the estimated trajectories, you can see that converge to the smooth values of real flows. The warm-up period is actually of no real importance for a Kalman filter because in a real system, we will continue running the estimator for a long period and we will not really face this phenomena again. So the results that we have for the case of estimating the density per lane are really good as well. We can see here the real density on the left and the estimated density on the right for on heat plots over the 4 lanes of the stretch for the same for the whole simulation period of 3 hours. And again, we can see that we have a very good match. Of course, more detailed results have been produced for the estimators and will be presented in a public deliverable that will be soon be published on the website, and it's going to be available for everybody. So let's turn our attention now to the traffic control algorithms, again for the case of mixed vehicle traffic. The automotive industry has mainly focused on designing algorithms that optimize the behavior of an individual vehicle rather than optimizing the overall efficiency of the traffic network. This vehicle-centric approach needs to be appropriately extended in mixed traffic conditions to also benefit traffic flow capacity and efficiency, particularly in heavy traffic conditions, as for example during rush hours at bottleneck locations. Appropriate novel traffic management concepts have been developed, which will enable the exploitation of existing or emerging vehicle automation and connectivity towards increased traffic flow efficiency. The algorithms that have been developed include the dynamic lane assignment for AV based on traffic conditions and penetration rates in order to serve the needs of scenario 1, while for the needs of scenario 3, which is related to bottlenecks, 3 strategies have been developed. The ACC time gap adaptation to maximize capacity and throughput in critical traffic conditions and in near bottlenecks. The lane change advice for individual connected vehicles aim to maximize the benefits for both individual drivers of connected vehicles and the overall traffic flow, and the mainstream traffic flow control via variable speed limits using VMSs and V2I communication. And this strategy aims to maximize traffic efficiency in mixed traffic. And this brings me to a poll question that I have prepared. So please let us know whether you are already familiar with any of these controllers by answering this poll. You can actually answer, pick up more than one answers, or if you're not familiar with any of them, you can pick up the last. We'll give you some minute, some seconds. Okay. Okay, now I will share the results of the poll. It looks like that the results are the choices are distributed more or less equally. ACC time gap adaptation has the most picks. Okay, we can possibly discuss that at the end. Let's now see some details and go back to the presentation and see some details for the controllers. The controller that we will first look at is the dynamic lane assignment, the DLA controller. This is a simple threshold-based control strategy that has been developed, and we consider a motorway stretch divided into a number of segments, and for the moment only one specific lane can be assigned to AVs as long as some conditions are met. The location of the lane, for example the right or the left lane, and the minimum number of consecutive segments that are required for the activation of a dedicated lane are pre-selected by the operator considering traffic management goals as well as safety parameters. And there is a predefined minimum period for activation. Adequate physical infrastructure adaptations have been developed by the co-simulation environment in order to achieve availability and consistency of information for all types of vehicles. So Conventional vehicles can be informed using VMSs at the beginning of each segment, while automated vehicles receive the information as well as specific lane change advices via communication well in advance. Let's have a quick view now on some conclusions that we can draw from the simulations. The whole set of results is presented in detail in the previously mentioned deliverable. First of all, we tried locating the dedicated lane to the right, the slow lane, but this had as a result a complete reshuffling of the traffic as the mixture of traffic used in the simulation includes a pretty high penetration rate of trailers, which are not automated. So we decided to use the fast lane for the implementation of the control action. And whenever the density of the network is pretty high, not necessarily close to the critical value, the reshuffling caused by the activation of the dedicated lane leads to excessive weaving and congestion that is created upstream of this area. Now, if we scale down the traffic and run the scenario again, we can conclude that the situation is beneficial for AVs, especially when the penetration rate of AVs is below 25%. And this is because we are using a 4-lane motorway and we are dedicating one out of the 4 lanes. But this is not the case for the rest of the traffic, and this leads to a deterioration of the calculated KPIs for the whole population. As expected, whenever areas around sets of on-ramps and off-ramps are included in the assignment logic, the results are a bit better compared to the opposite case. Of course, this is due to the fact that the lane assigned is always the fast one, and inclusion of these areas leads to assignments that continue throughout the network without interruption that may lead to more weaving. So let's have a look now to some results that we've got for the bottleneck scenario using the first controller mentioned before, the ACC time gap adaptation controller. The main philosophy behind the proposed concept is to leave the ACC settings untouched at the driver selected values if traffic is clearly under critical. And we do that so as to limit intervention only to traffic situations that call for efficiency increase. And change the SEC settings, in this case the time gap used, gradually as appropriate to improve the flow efficiency when critical traffic states are imminent or present. The proposed control strategy is only dependent on real-time information about the current traffic conditions and is actually activated only when, where, and to the extent that is actually necessary. Here is an example from one out of the 10 replications that we conducted for a 45% penetration rate of connected vehicles. On the left heat plot, we have the speed for the whole motorway stretch over 3 hours of simulation. Congestion appears at this area after some 50 minutes, and we get this spillback of congestion. The use of the controller that is changing the time gaps to be used by the connected vehicles that are supposed to be equipped with the ACC system has as a result the complete removal of the congestion, as you can see on the right-hand side. If we now increase the penetration rate of connected vehicles to 70% by increasing the penetration rate of both connected conventional vehicles and automated vehicles, we get more congestion because of the presence of more automated vehicles. So on the left, the heat plot, we have the speed for the whole motorway over the stretch, and again we can see that the controller, with the results on the right, is taking advantage of the higher penetration rate of connected vehicles and is able to remove the congestion by suggesting lower time gap values. Here I have included
I'm sorry to interrupt you, but please be aware of the timing.
Yes, I am. Here are some details about the default time gaps used for the different classes of vehicles included in the simulation. the default value is 1.4 seconds, which is much higher than the values used for conventional vehicles. If the minimum time gap that can be suggested by the controller is 1 second, then we get more than a 40% improvement on vehicle delay for the high penetration rate. And in all cases, the congestion is fully removed. However, the percentage of improvement for the low penetration rates is smaller, as the congestion, that is the real problem that has to be removed, is smaller. Now, if the minimum time gap suggested by the controller is 0.8, we can improve even more, and we reach some 50% of improvement for the vehicle delays, or 15% of improvement for the average travel times, and 17% of improvements for the speeds. And this is my last slide. I will just give a short introduction for the mainstream traffic flow controller, as the following presentation includes evaluation results for the controller. The main purpose of this controller, of the mainstream traffic flow control, is to enable the mainstream traffic flow that is approaching areas with particular infrastructure layout, as bottlenecks, merge of on-ramps or lane drops, to take values that will allow the establishment of optimal traffic conditions for any appearing demand. And this is done using density measurements from the bottleneck area and a PI regulator that is trying to attain the density around the set point that is selected to be equal to the critical density in order to achieve flow maximization. Of course, some VSL practical implementation aspects have been taken into account. And with this, I would like to conclude my presentation. Thank you all for your attention. I think that we still have some time for a quick question. Thank you.
Yes, thank you very much, Yannis. Since we are a bit over time, I would like to ask you or read one question we have received. And the question is, what are the main sources of data for the estimation algorithms?
The main source of data is speed from connected vehicles per segment. So the connected vehicle speeds are a very good proxy for the actual speed on each segment. And we also use flow measurements appropriately located, flow measurements from spot detectors, in order to guarantee observability of flow, which means that in between two unmeasured on-ramps or off-ramps, we have to use a mainstream measurement.
Okay, thank you. And then I would give back to Anna-Rita.
Okay, thank you, Ioannis, for your presentation. And I would like right now to introduce my colleague Karl Schrapp. He's a researcher at Fraunhofer Focus, and he will give a presentation on microscopic simulation. Okay, Karl, the floor is yours whenever you're ready. Karl, I can't hear you. Okay, now I can see your screen. Now. Okay, good. Okay. Now I can hear you.
There was just an interruption. my GoToWebinar froze for a moment. So hi everybody. My name is Karl Schrapp. I'm from Fraunhofer Focus here in Berlin. And I'm since 5 years now already one of the main developers of wait a moment, now it's working?
Yes, now I can see your presentation.
I'm sorry. One of the main developers of our co-simulation framework, Visum ATI. which we used here in the INFRAMIX project for the microscopic simulations and evaluations, and also that he agreed the results which you have seen in the previous presentation have been conducted using this very framework. So I will close my and we'll start with my presentation. So first of all, the microscopic simulation, microscopic evaluations we did with our co-simulation framework has some requirements. We have to draw from the big picture you may already know. So first of all, we needed some kind of digital map to include into the simulation. We needed some kind of traffic vehicle modeling. So we not only have connected and conventional vehicles, but also automated vehicles and so on. Additionally, we have infrastructure to include, so variable message signs and also road infrastructure sensors. We have communication to include into the simulation. For example, we have to include the ITS-G5 communication to enable communication between roadside units and vehicles, but also communication to via the cellular link, for example, via LTE or 5G. One of the main issues or challenges we had was to integrate the estimation and control algorithms, which also have been implemented in the field, which have just been presented. And of course, for that, you need some kind of interface which enables that the traffic estimation control algorithms receive measurements from the sensors and also measurements from the vehicles, from the connected vehicles, and on the way back to set control decisions on the VMS, variable message signs, and also to send specific advices to the vehicles. So we did that with our INFRAMIX co-simulation environment, which is basically an extension of the software Visum RTI, which has been developed since 10 years now by us, the vehicle to X simulation runtime infrastructure. And the main idea here is to couple various simulators from various domains to a big simulation tool. And I will now jump through some of the key aspects which we covered with the score simulation environment, starting with the main important thing is the traffic simulator. So the traffic simulation takes care of simulating each vehicle individually with rather simple models in order to have simulations running with more than 1,000 vehicles simultaneously. We used the simulator Sumo for that. But since our simulation environment allows to exchange those simulators for future work, you can easily exchange this as you need. Then we have an application simulator running, which takes care of several things. One thing is the different modeling between conventional vehicles, connected vehicles, and automated vehicles. And secondly, to enable the integration of the traffic estimation and control algorithms, which allows us to simulate sending out speed advices, gap advices, lane change advices, and also to set specific advices for conventional vehicles by setting variable message signs. Then we have communication simulators integrated into the environment, which allows us to simulate ITS-G5 communication. Here we can use either a rather simple model, which allows very fast simulation, or you can also use more detailed models, for example, the open source simulator Omnet++. And for the cellular communication, we use an own implementation which allows us to simulate cellular communication via LTE or 5G. Then we have a VMS simulator, which gives us the possibility to set dynamic signage. So we can set speed limits for each lane individually, and also allows us to assign lanes to automated vehicles. And last but not least, we integrated another co-simulation framework into our co-simulation framework, which will be presented after my presentation, which is ICOS, which allows to model one vehicle in very, very great detail, where you have several models for one vehicle. Some of the key aspects we have modeled in the simulation, which were rather new, yet now here for INFRAMIX, is for one thing the highway segmentation we modeled, where we split the highway into several segments, where each segment is starts or separated with a gantry where we place variable message signs, for example, but also road sensors like spot sensors and camera sensors to measure density and flow. We have different communication links enabled, like I already said. We have models for the traffic services, which have been presented by Daniel at the beginning. And we have different models for conventional automated vehicles. So we model exactly how they react on the devices, how they react on VMS signage, and so on. And of course, we have the traffic and estimation and control algorithms, which have been implemented in the field, integrated directly into the simulation to have some kind of software in the loop here. Next to the simulation environment, you need some kind of scenario. At least we call it always a simulation scenario, where you define all those aspects. So one key part of this is the traffic model and the road model. So what we did was that we transferred the digital map, which we had from the Girona 87 test site, into the simulation, divided those test sites into 40 segments with 500 meters each, placed gantries and spot sensors at the road for the simulation. And in the next step, we created a traffic model based on toll data, which have been provided by Abertis, which allowed us to create a calibrated traffic model with 125,000 vehicles during a whole 24-hour day, with 80% of cars, 11% of trucks, and 2% of motorcycles. And we actually can vary the penetration rate now of conventional, connected, and automated vehicles individually. And secondly, finally, let's say, the result was this traffic model, which forms this congestion you have already seen near segment 30, which is around 15 kilometers of the stretch. The idea is now, of course, by the controllers to avoid or dissolve this congestion with the presented control strategies. And one of those control strategies was the VSL control, the mainstream traffic flow control via variable speed limits. And we did, next to TUCrete, we did some evaluations on that, which I now want to show you. So first of all, we wanted to know how many variable message signs do I really need so that the VSL controller for conventional vehicles is still working. So we had basically 3 configurations. In the first one, we do not have any variable message signs at all, no control algorithm actives. In the second configuration, we placed the variable speed signs on each segment, so in 500-meter distance from each other. And in another configuration, we placed only a few segments, only a few variable speed signs between on the road. What does a few segments mean, or few variable speed signs mean? We place them at strategic positions. In total, those are 5 VMS between 2 on-ramps. And the results are the following. So in the no control case, we have rather bad congestion evolving at segment 30. And if you place the full VMS or only a few VMS, the VSL controller is actually able to avoid the congestion to form by setting by reducing the speed at a specific point of time according to a density, critical density reached here. The speed is reduced, and therefore congestion could be avoided at this point. And at least in that case, it doesn't really matter if you have VMSs at every 500 meters or VMSs at strategic positions. In average, and also with different penetration rates, you save around, or you can improve the traffic efficiency about 14%, whereas when you have only few VMS, you can improve traffic efficiency by 8 to also 40%. It depends a bit on, or at least in that simulation series we did, it largely depends on the performance of the no control case. However, more details you will find also in the deliverable if you are interested in. In another evaluation, we try to find out what is if we do not use any variable message signs at all. So we want to do not invest into infrastructure. However, we still want our controller to be active. So the idea is that we do not have the variable message signs anymore, but only static signs, classic static signs. And the idea is that we send speed advices to all connected and automated vehicles with the hope that the little portion of vehicles which receive those speed advices have impact on the whole traffic, and therefore reduces the speed and increase the flow at the bottleneck. So for that, we already again had some configurations running. For one thing, again, the no control case. Then we had 2 configurations for the ITSG5 case, where we placed roadside units in a very close distance to each other or very far distance to each other. And another case where we do not have any roadside units, where we used cellular communication to enable this controller. And again, even without any variable message signs and only connected vehicles receiving the advices, the VSL controller is able to work, as you can see here. However, this is highly dependent, of course, of the penetration rate, as you can see here. So with rather low penetration rates, you do not get this high improvement in traffic efficiency. But if you use here in the middle, for example, 30% of connected vehicles you already receive very similar results as you get when you use variable message signs, just by sending advices to a small portion of vehicles. So concluding here in our work in INFRAMIX, we developed this comprehensive co-simulation environment based on Visma TI, which allowed us and all other partners to conduct several evaluations and testings of the controllers and functions. For that we provided two simulation scenarios, one now here for AP7 Girona, which I presented, but also one simplified simulation scenario for the Austrian test site. And additionally, we showed or analyzed how the infrastructure and communication is required to get the VSL controller work, and again in the deliverable, which will be on our website soon, you can find all the results. So thank you very much. If you have any question, Martin.
Yes, thank you very much, Carl. And I would like to ask one question. So the question is, what will be would be the next steps and the effort to extend the simulation also to other types of streets or areas?
What exactly do you mean with other types? Also, you mean more or less you can use the simulation framework on any type of streets, right?
Yes.
It of course depends on the model you are using and on the. What do you actually mean with other types of streets, or do you mean other locations?
Yeah, other locations and also other areas, so maybe rural areas or even urban.
Yeah, I mean, we are using this simulation framework already for different areas. So we are using that not only for highways, but also for urban areas and also rural areas. And especially apparently the traffic simulator we are using here, Sumo, it depends mainly on this on the traffic simulator, right? Is able to model urban areas, but also with multimodal stuff, so you can integrate persons and public transport as well. So it mainly, the simulation framework is not limited at all on the area, so you can use that everywhere.
Okay, so thank you. And I would then hand over back to Anna-Rita.
Thank you so much, Carl, for your presentation. I will give now the floor to Martin Rudiger. He's a researcher at Virtual Vehicle, and he will give a presentation of submicroscopic simulation. So, Martin, I hope you're ready. I can see your screen.
Thank you. Can you hear me now?
I can hear you.
Thank you. My name is Martin Rudiger. I'm a researcher at the Virtual Vehicle. I'm expert in control systems. Yes, and I will give you a presentation about submicroscopic simulation. First of all, I want to give you an overview about the content I will talk about the next 15 minutes. I will start with an introduction about submicroscopic co-simulation. Then I will talk about the co-simulation of microscopic and submicroscopic simulation. Then I will give you an overview over the used modules of the submicroscopic simulation. After that, I will talk about the characteristic of submicroscopic co-simulation. Then I will come to a part which deals with the scenarios.
I will first talk about the simulated road in the traffic before I will introduce the 3 scenarios and give some results. Submicroscopic co-simulation framework. The submicroscopic co-simulation framework consists of 2 main parts. The microscopic simulation part, like Focus has presented, and the submicroscopic simulation, which is our part. In the microscopic simulation, a huge number of vehicles are simulated, together with infrastructure and infrastructure-to-vehicle communication. In the submicroscopic simulation, only 1 automated vehicle is simulated, but this vehicle in detail. This simulation consists of vehicle dynamic simulation, sensor simulation, simulation of automated driving functions, and the road. And all these parts are coupled via co-simulation, so that the vehicle under test can react on the traffic of the microscopic co-simulation and vice versa. Let's have a look at the modules of the submicroscopic simulation part. The first module is a vehicle dynamic simulation model of the vehicle under test. This model gets its driving commands, pedals, and steering angle from the automated driving function. The driving states, position, velocities, and accelerations are passed back to the driving function and are also transmitted to the microscopic simulation, which needs the information where the vehicle under test is driving and which velocity it has. The position is also passed to the static environment. Around this position in this module, information about lane layout and traffic signs is generated. This information is transferred to the sensor. The sensor module also gets information about the surrounding traffic from the microscopic simulation. The sensor picks up the relevant information and passes it to the automated driving function. Another module is dynamic data. It gets infrastructure to vehicle messages from the microscopic simulation and passes them to the automated driving function. Now I have a short question for you. Sorry. What do you think are the benefits of the submicroscopic simulation? Possibility of modeling of every traffic object, implementation of realistic vehicle dynamics, real driving functions can be used, different sensor models can be used, and all of the above. Okay, the number is not increasing anymore. And I will close the poll. Or should I? Yes. Before I will come to the next part, a short summary of the characteristic of submicroscopic co-simulation. In macroscopic simulation, we have a huge number of vehicles, but the low details on vehicle level. It's a good method to simulate traffic, but you can't look into the details of one vehicle. On the other hand, submicroscopic simulation. We have only one vehicle under test, but with a detailed vehicle dynamic model, we can also have detailed sensor models, advanced driving assistance functions, and automated driving functions. And both are coupled via co-simulation to get the best of both worlds. The next part of my presentation deals with the scenarios and results. Here we'll start with a description of the simulated road stretch. This is a part of the Austrian test site near the airport of Graz and has three lanes. We've divided them into 4 segments and will concentrate on segment 3, where the on-ramp is. We got traffic data from ASFINAG and derived out of the data the following. We use 4 levels of services to find the traffic density. Level of service A, which means free flow, is defined with 1,580 vehicles per hour. Level of service B with 3,065 vehicles per hour. Level of service C with 4,410 vehicles per hour. And level of service E with 5,180 vehicles per hour. 85% of the vehicles in the data sample were passenger cars. We divided them into conventional vehicles and automated vehicles. 1/4 was defined as automated vehicles. This leads to 64% conventional vehicles, 21% automated vehicles, 2.3% motorcycles, 4.7% trucks, and 6.9% trailers. The first scenario in submicroscopic simulation is bottleneck on-ramp. The mixed traffic starts on the main road before segment 0, and then the vehicle under test starts at the on-ramp, accelerates and tries to merge into the traffic on the main road. We made a baseline simulation and 2 measure simulations. In the baseline simulation, the vehicle under test tries to merge into the traffic on the main road without help of the infrastructure. Against this simulation, the measure simulations were compared. In measure 1, the speed of the traffic on the main road was reduced to 100 km per hour. This was done via a variable message sign for the conventional vehicles and also for trucks and trailers, and via IVM speed advice for the automated vehicles. In measure 2, the speed of the traffic is also reduced to 100 km per hour with the same infrastructure as before, but additionally, the automated vehicles receive a lane change advice to the left to build up gaps for the oncoming traffic from the on-ramp. Only the short period where the vehicle under test comes from the on-ramp and merges into the traffic of the main road is of interest for our observations. This means that per simulation run, we have only a small time slot of 30 to 60 seconds to investigate. Therefore, each of these scenarios was repeated 60 times and the results were compared. Now to some results of the first scenario. First of all, the measured traffic density. The upper table shows the demanded and measured traffic density for the different levels of services. We can notice that the results match well. The lower table shows in how many of the 60 experiments the vehicles under test was not able to merge into the traffic of the main road and had to come to standstill at the end of the maneuver zone. This was in level of service A and B, never the UKs. With a higher traffic density, it occurred. In level of service C, the measure has nearly no effect. In level of service E, there are 7 stops in the baseline and measure 1, which is only the speed advice. But in case of measure 2, which has also a lane change advice to the left, the number of unwanted stops decreased to 2. Next slide shows some results in the traffic efficiency. Mean speed. The left diagram shows the mean speed of conventional vehicles in segment 3 for 3 different simulation types. For the baseline in blue, for measure 1 in red, and for measure 2 in yellow. Obviously, the mean speed decreases due to the measure. First, the speed is limited to 100 km per hour, which has the greatest impact. And in low traffic densities, but only a small impact in high densities, because the mean speed is already lower than the new limit. But the lane change advice has big impact in high densities. An automated vehicle has the speed advice nearly no impact, but for the lane change advice, it is the same as with conventional vehicles. The mean speed decreases in higher densities. The additional lane changes to the advice slow down the traffic. The results on travel time show the same as on the mean speed. Only the travel time goes up where the mean speed decreases and vice versa. Now to the next scenario, bottleneck main road. We use the same road stretch as before, but now the vehicle under test starts at the main road and is faced an on-ramp where 10% of the mixed traffic came from the on-ramp. Again, we simulated a baseline scenario without infrastructure measure and the same two measure scenarios. In the first measure scenario, the speed on the main road was reduced to 100 km/h. The conventional vehicles were informed via a variable speed measure sign, and the automated vehicles received the speed advice via an IV message. In the second measure, additionally to the speed reduction, a lane change advice to the left for the automated vehicles were sent. This should build up gaps for the oncoming traffic from the on-ramp. First, a look on the traffic flow. When comparing the demanded traffic flow with the measured traffic flow, it can be seen that in higher traffic densities, we have problems to generate the demanded traffic. Here are the mean speed of this scenario. The left diagram illustrates the mean speed of conventional vehicles in segment 3 for the baseline, as well as for both measure simulations. The mean speed value decreases with increasing traffic. It can be seen that the mean speed is reduced in the measure simulation due to the speed advice, which is also active in the second measure simulation in case of the lane change advice. Automated vehicles move away from the first lane and cause a higher traffic volume on the second and the third lane, which results in decreasing mean speed furthermore. As the mean speed of automated vehicle is lower than the speed advice, measure 1 has nearly no effect on mean speed of automated vehicles. But at the level of SE, the lane changes due to the Anna-Rita, can you hear me? Because I have a message that my...
Yes, I can hear you.
Okay. Since the mean speed of trucks and trailers is also lower than the speed advice, the measure 1 has nearly no effect. And trucks and trailers are not affected by the lane change advice. Also, measure 2 has no effect on trucks and trailers. Now to the third scenario, the roadwork zone. In segment 3, the rightmost lane was defined as a roadwork zone and is blocked. Only 2 of the 3 existing lanes remain available for the traffic, and the on-ramp is also closed. The vehicle under test and the mixed traffic drove on the main road. As baseline, we defined that the vehicle under test must recognize the roadwork zone with its own sensors and then try to merge into the remaining 2 lanes. In the measure, the vehicle under test is informed via an infrastructure to vehicle message about the oncoming roadwork zone and can early begin to search for a suitable gap for a merge maneuver. In contrary to the other scenarios, this time only the vehicle under test is influenced by the measure. This means we will not have a big impact on traffic flow and efficiency to the measure. The traffic flow was measured with a detector about 300 meters after the beginning of segment 3. The starting point of segment 3 is also the starting point position of the roadwork zone, with only 2 drivable lanes. First, it must be said we have not calculated new level of services. The loss rates are valid for areas without a roadwork zone and not for the areas with roadwork zone. Nevertheless, here are the traffic densities. In loss A, and B, we reach the demanded traffic flow. But in loss C and D, the capacity of the road which is reduced to 2 lanes, is not sufficient for the demanded traffic. And in segment 2, the segment upstream of the roadwork zone, congestion is built up. Let us concentrate on the vehicle under test. The vehicle under test has to merge into the remaining two lanes because the rightmost lane is closed. But not in all cases this means a lane change, because in some cases the vehicle under test drove on the middle lane or the left lane when it faces the roadworks on, because it had overtaken slower vehicles. This is the cause why the sum of stopped and merged are not the number of experiments, which was 60. In the baseline, in all traffic flows, the result was nearly the same. 3 times the vehicle stopped and about 30 times the vehicle merged. The measure simulation. In lowest traffic density, the vehicle never stopped and merged 27 times. In this case, the measure was successful. In level of service B, we have a problem. Only 5 times the vehicle drove on the rightmost lane, and therefore the sample is too small to make a statement. In level of service C, it's a little better, but still not good. The sample of 14 is very low. In the level of service E, there seems the measure has no effect. I think this is due to the congestion. Then there are no gaps available that can be used for the vehicle under test. Conclusion. We have constructed a co-simulation framework consisting of microscopic simulation parts and submicroscopic simulation parts. The microscopic simulation is with its full traffic model, but lack of detail in the vehicle level, including infrastructure and communication, and the submicroscopic simulation with a detailed vehicle model, but only on vehicle which consists of a vehicle dynamics model, sensor model, automated driving function, and static environment, which means road and sands. Then it described 3 scenarios and gave some results. Thank you for your attention. Are there any questions?
Thank you very much, Martin. I would like, since we're still a bit over time, I would like to ask one question. And the question is, what about the implications for different car manufacturers? Will the results differ between different manufacturers? Because every driving function and vehicle is different.
Yes, the result will differ. As you said, every car manufacturer has its own strategy. In some points, they are similar, but there are always differences. This means the vehicle under test will react differently, and this will influence the whole simulation and results.
Okay, thank you very much. Then I would like to give back to Anna-Rita.
Okay, thank you, Martin, for your presentation. This is the end of our morning session. So many thanks to all attendees for joining us. And again, this session will be will be available in a recorded mode, and then also all the presentations by our speakers will be sent in a follow-up email. So thank you everybody for joining. Please have a look at the handout where you can find some more information about our contacts on social media and website, plus a poster if you want to have a look at all INFRAMIX main scenarios and solutions. We'll be back at 13:30, so you have time to have lunch, grab a coffee, and yes, we will be happy to welcome you again in 1 hour and a half. Thank you. Hello everybody, welcome back to INFRAMIX panel event. This is Anna-Rita. For those of you who haven't joined during the morning, please be welcome to our final event, and we will soon be starting our afternoon session. Please be reminded that your questions are always very welcome. Please use the question box on your right to type your question. Please do not raise your hand because we won't have time to hand the microphone to you. As a reminder, also please be aware that all attendees are muted by default to avoid background noises. And also, please have a look at our handouts. Here you can find a very previous introduction on the GoToMeeting tools. And then there's also the webinar agenda, so you can check the timing and the speakers. There's also data protection statement. Please be aware that this section is being recorded. And also there's an INFRAMIX poster with all the information on the 3 traffic scenarios, the partners, and the solutions we elaborated during the project. Very well, so I would like right now to introduce my colleague Selim Solmaz. He's Senior Research Engineer at Bit4Vehicle. Selim, I hope you're ready.
Yes, I'm ready.
The floor.
Yeah. Can you see my video? Could you please confirm?
Yes, I can. Yes,
okay,
I can.
Perfect. So thank you for the short introduction. Yes, my name is Selim Solmaz. I am employed at the Virtual Vehicle Research Center in Graz, Austria. And I'm working in the Department of Electronics, Electronics and Software, and particularly in the Control Systems Group, and mainly working on the automated driving related problems as part of my work here. And in this respect, in INFRAMIX project, we have done some work related to our responsibilities in this department, and I'd like to introduce them to you. So let me share my screen. Could you please confirm if you can see my PowerPoint window, Anna-Rita?
I can see your screen and PowerPoint, but it's in presentation. It's not in presentation mode.
Yes, I'm switching it on. Sorry.
Good, very well, perfect.
Okay, so let me get started. Sorry. Okay. Today I'm going to talk about hybrid testing, which is a vehicle-in-the-loop methodology for evaluating automated driving functions in virtual traffic scenarios. That we so it's a methodology we developed in the scope of INFRAMIX project, and I'd like to introduce this to you. But before we start, I would like to just out of curiosity and also to get everybody involved. I just have a poll question about your ideas about how difficult would it be to test and validate automated driving functions in comparison to existing safety systems for vehicles. So I just started my questionnaire. I hope you can see it now. I'm seeing that there's some answers coming already. So just your ideas about the difficulty in testing automated driving functions, whether they should be similar to existing safety systems such as ABS, ESP, passive active safety systems, or would they be more involved? And this is also irrelevant to your background. You can be from the area or not. Of course, it would be more relevant if you're from the field, which I think it is. So I think, yeah, we are still receiving some votes. Okay.
Selim, I apologize if I step in. Just a quick reminder for attendees. In case you experience any difficulties with the polls, please switch on and off the full screen mode. Because apparently we're having some problems with that. So either it's working on full screen mode or Windows mode. Thank you.
Okay. Thank you very much, Rita. So I think most people who wants to vote voted already. So let me close the poll and let me show you the results. So just this is interesting that most people think that it is way more involved than standard active safety systems, which is also the view that we share. And in response to this, we would like to actually show you a methodology which can actually answer this question. So let me go back to my presentation. Can you see my presentation screen again? Could you please confirm?
No, really, Selim.
Sorry?
Not really. Maybe you need to hide the poll. Okay, now I can see your presentation. You should start the presentation mode again.
Okay. So you should be seeing it now.
Good, very well.
Okay, so let me start with the hybrid testing methodology and concept. Basically, a hybrid testing concept is based on the co-simulation framework that is introduced by my colleague, Martin Rudiger, earlier in the first half of the conference, the last presentation. So this is a co-simulation framework where we can use dedicated software components to implement certain scenarios for testing. And here we are increasing the realism of the submicroscopic simulation by replacing the vehicle dynamic model and the driving functions with the real hardware itself. So here you see a concept description of this concept where we have the actual test vehicle from virtual vehicle that is actually fully open. We can control the steering, braking, and acceleration of the vehicle. It has onboard processors that can be programmed, and these include the driving functions we design. And also we have real communication hardware that is able to communicate with infrastructure roadside units. The rest of the traffic scenarios are to be implemented in a virtual way, like the same way, actually in the same way in the submicroscopic simulation, with simulated traffic scenarios implemented in Sumo traffic simulator, a static environment defining the road and the signage and everything related to the driving scenario, a vehicle sensor module, and dynamic data. And we can combine this virtual and real components to make the car believe, this automated capable car believe that it is driving in a very specific driving scenario. Here are the specific components that we utilized for this purpose. Basically, the vehicle is a fully capable automated driving demonstrator vehicle. So it's a Ford Mondeo test vehicle that we have in-house. And it has an ADAS kit by DataSpeed company, which allows us the access to the onboard sensors as well as the controls of the car. On top of this, it's of course equipped with a number of additional sensors, but none of these were utilized in the scope of INFRAMIX project because we were aiming to virtually represent this sensor data with our co-simulation framework. The only sensor that we utilized in hybrid testing implementation is the highly accurate GPS, directional GPS system. It's a dual antenna GPS system providing high accuracy position, heading, and velocity, which we can utilize in the scope of the implementation. We also have a real-time controller from MicroAutobox. In this, we implement our driving functions. Actually, these are the same driving functions utilized in submicroscopic simulations, except that these functions are actually exported in the real-time code to run on the MicroAutobox system to gain control and the control of the vehicle. The rest of the system is implemented on an onboard PC that you see on the right bottom. So this is including the blue box in this illustration. In this one, we have the dynamic, basically the static and dynamic environments, the traffic scenario, the sensor model, and communication with the rest of the vehicle. Also, we have an interface to an onboard unit, which can send and receive information to the roadside unit in the form of ITSG5 messages. And in this structure, we can implement our hybrid testing solution. For the hybrid testing solution, we have done a proof of concept implementation in Graz, near Graz. Actually, it's a proving ground, 30 kilometers south of Graz city. And in this proving ground, that you see on the top from satellite view, we have designed a digital map of this test track to implement with our driving scenarios. Of course, the size of this test track is quite limited, so it's in total about 300 meters, and 250 meters is usable for us for this purpose, but it has 4 usable lanes and up to about 10 meters width. So we utilized 3 lanes of this proving ground in digital form and designed our experiments accordingly, which we'll see next. In the scope of the prototype implementations, we have done 2 experiment stacks. In the first experiment stack, we have implemented a scenario based on an on-ramp merge scenario. So the vehicle will start on the on-ramp and then try to merge to the main road on the left. And we have looked at cases where there's no traffic, where there's low traffic and high traffic. And in the second stack of experiments, we have implemented a main road start of the vehicle under test with a speed recommendation sent by the roadside unit. Again, we looked at a case with no traffic, the vehicle under test alone, with traffic, with speed recommendation, and various conditions depending on the density of vehicles in the scenario. Here's the first example of how it looks like. So in this first example is the simplest scenario we have, that we are starting on the first lane, which is the actually second lane from the right, you see. So vehicle under test is starting on this lane from 0 velocity and accelerating to 30 kilometers per hour. When it reaches 20 kilometers per hour, which is a design parameter, it starts a lane change and merges into the lane 2, which is the lane on the left, and then again on the lane on the left, which is the third lane. What you see on the center of the screen is the sumo representation of the scenario. The vehicle under test is blue, so maybe it's not very visible on this, but maybe in the further videos we will have a better view of this. So there's no interfering traffic, and the vehicle is conducting the commanded actions without a problem. Just want to mention that the motorway chauffeur that is referred to later is running on the real-time controller on the vehicle, which implements a lateral controller, a longitudinal controller, and a trajectory planner to conduct these maneuvers. So here is the output that we can obtain from this specific scenario. So this is obtained, of course, from post-processing by combining data obtained from the vehicle, from the microtobox system, and also from the Sumo traffic simulator as implemented in the scope of the co-simulation framework. This is the longitudinal dynamic output, so we can see the variation of the vehicle speed to the commanded speed of 30 kilometers per hour, of course here represented in meters per second. And in the bottom, you see the pedal and brake action during this experiment. And on this figure, we are looking at the trajectory of the vehicle with respect to the digital map. And here is an example of the lateral dynamics outputs obtained from the vehicle sensors. And the typical vehicle sensors that we use in vehicle control systems design is yaw rate, lateral acceleration, and steering wheel angle, which is shown as an example, but we have access to full range of vehicle data in this scope. Here is this second representation or second experiment, where in this case, it is the same scenario as before, but we have interfering vehicles. So there are 3 vehicles in this case. Again, I hope you can see the video in a clear way. What you see on the sumo representation on the center is that there are 3 object vehicles, and the vehicle under test is starting behind. As the front vehicles are fast enough, you don't see any change actually. So there is no interference with the vehicle under test with the object vehicles, and it can actually conduct its designed maneuver without a problem. So this is the micro-autobox control desk. You see there are many computers running in parallel to realize this solution. In the next experiment, we are looking at the same scenario with a high density traffic. Of course, since this is a very restricted testing ground, high density is just 10 vehicles, as you will see. So it is the same scenario. The green vehicles are simulated vehicles and blue vehicle is ours. And the motorway chauffeur is trying to find a gap to join, to merge onto the main road, but since it's too dense, it cannot conduct its maneuver. And as designed and required, we make it stop. Okay, so this was an example where we could test the functioning of the motorway chauffeur in some example scenarios. Next is an example experiment where we utilize IVI message. So this is an infrastructure control message, which was also mentioned by the first one of the first presenters in the morning by Siemens. And I'd like to mention that these experiments were conducted with the help and support of Siemens, as they provided a roadside unit at the test site to provide the IVI messages. So on the left, you see what we have looked at before, and on the right, in the scenarios, we will send a recommended speed advice and see how it changes the vehicle behavior. So in this scenario, the vehicle will start on the main road and a max speed, so the vehicle will be starting in the same way, and a speed advice will come, and we will look at this with and without traffic. So in this case, again, the vehicle is starting on the main road. This is not a mercenary anymore. There is a front vehicle. So we are just trailing this car. So at the middle of the road, it receives a speed recommendation of 50 kilometers per hour. And since it is faster than the front car, it's conducting a takeover maneuver. So this is a lane change maneuver commanded by the trajectory planner in response to the IVI speed recommendation. Again, so in this example, it's the same scenario, but instead of the speed recommendation of 50 kilometers, we command a smaller speed, which is not sufficient to conduct a lane change maneuver. And you'll see that the vehicle will stay behind of the front vehicles and not conduct a lane change. So this is the commanded lane change. But since there are no gaps to the front and the front vehicle is not slow enough, there will be no further lane change maneuvers. So it will just follow the front vehicle. So the motorway chauffeur in this case is adapting its speed. So let me show you how it looks like. From the Sumo perspective, you see the over-the-air car data obtained from Sumo of the same scenario. We have 4 target vehicles shown with empty rectangles, and this solid rectangle car is our vehicle under test. So it is receiving an IVI message, which you see here. So this is the commanded speed. So it was 30, and at about midpoint, it is receiving a speed recommendation of 40 kilometers per hour. But since it cannot pass or overtake the front vehicle, it is actually trailing behind the front vehicle, which is traveling slower. Again, you can observe this from the brake and throttle signals below. for each experiment step we have conducted in this respect, we looked at some key performance indicators. So here's an example which we show in this table. We have a number of tables like this, which we report in an upcoming deliverable at the end of the project for the evaluation of the results, the deliverable 5.3. So we are looking at conditions like whether an IVI message sent and received, what was the sent IVI recommended speed, whether vehicle under test has adaptive speed or not, what is the mean speed in the relevant zone and overall, and mean speed overall, minimum distance gap, minimum time gap, and minimum time to collision. So these are relevant parameters to help analyze the safety and efficiency related aspects in this respect. So with that, I'd like to come to the conclusion of this first presentation. Basically, with this implementation, we have demonstrated repeatable and stable real-world proof of concept test runs with our test vehicle at the UMTS Liebring Proving Ground in Graz. We have collected data and proof of concept is demonstrated. And we have also publicized these results in a number of conference and journal publications. And we have also conducted comparisons between submicroscopic simulations and hybrid testing, which are quite interrelated. And so we actually conclude that the methodology is particularly suitable to evaluate ADAS functions in various randomized traffic scenarios. And there are, of course, other potential utilization, especially for testing the effect of CITS messages on mixed traffic scenarios, which are normally not very easy to conduct in real-life driving scenarios or conditions. And at the end of this project, we are thinking of potential extensions, of course, depending on the project, upcoming projects, where we will look at modeling sensor models in the scope, 3D visualization integration, so that we can use this methodology together with some perception algorithms for automated vehicles, and integration of vehicular sensors to the co-simulation framework, with which we can enhance the actually driving condition by combining vehicular sensors as well as the simulated ones. And we can use this overall methodology to obtain digital twin calibration results, with which we can obtain very highly accurate simulations of real life. So with this, I'd like to come to the end of my presentation. And let me see, I think time-wise we are okay. If there's time, I'd like to pose another short poll, if possible, which is quite interesting for me to hear the result. To Anarita, do we have enough time?
Don't worry.
Okay, yeah. Okay, so let me start the poll again. So I would like to know what is your idea about how useful would this introduced methodology for testing ADAS functions and solutions for connected automated vehicles? What would be your feeling? So I'm seeing very positive results. Thank you very much. I don't think it is the best solution ever, but the ones who choose this, really thank you. I think it can be extended in many, many ways. Okay. So I think there are no more answers. So let me close the poll and show you the result. Yeah, okay, most of you think that it is a methodology that can enrich existing testing options, which is very positive from my side, which is very actually expected. And I'd like to thank you for this. And with this, I am almost done. Actually, we have a video we would like to show in this presentation, but so I don't know if there's enough time for this. I think this video is a promotional video is available in the handouts. Anarita, could you please confirm?
Yes, this video is available already. So I would rather skip to any questions that might have come.
Okay.
Martin, can you please help with that?
Yes. So I would like to ask you one question, and the question is, how does the methodology differ from existing vehicle-in-the-loop implementations? In what ways the hybrid testing methodology could be extended?
Okay, so basically there are also other vehicle-in-the-loop testing options that have been introduced in the literature. The main difference is the co-simulation framework that we utilize. In all of the existing systems, there is a test vehicle, but we have not seen many examples where there is the co-simulation framework implemented. And the main benefit in this is that you can utilize dedicated software tools that can be developed in some random interface and some random language. These can be readily integrated into our solution. So we can actually test a commercial driving function from a car manufacturer without really knowing the details of this. So we can embed this driving function as a functional mode interface, FMI, into our framework and test its response in comparison to ours in a simulated scenario. So this is I think, very unique. And how we can extend it is what we wish as a first step is to extend it for the sensor modeling. So at the moment, our sensor model is quite simplistic. We have a sensor cone, and if a car or any object gets into this sensor cone, then we actually know what it is. There is no sensor dynamics implemented, and at the first step, this would be a natural extension for us to investigate.
Very well, thank you for your answer, Selim. And
Welcome.
I thank you for your presentation as well. And I would like right now to leave the floor to Stamatis. Stamatis Manganiaris, he's a senior researcher at ICCS, and he will share a presentation about users' appreciation.
Thank you.
Okay, Selim, now I'm sorry, Stamatis, now you should be able to
okay.
share your screen.
Okay. Hello, everybody. I warmly welcome you to the final conference of INFRAMIX. My name is Stamatis Maganiaris, representing ICCS National Research Institution of National University of Athens and the technical coordinator of INFRAMIX. So,
Stamatis, I guess you are sharing your camera, but I can't see you.
Yes, it was a problem, obviously.
Okay, very well. Never mind.
Okay, so you see my screen now?
I can see your screen.
Okay. So our topic is do you still see it or not?
Yes, I can still see your presentation.
Okay. So our topic is about user appreciation. There is a problem, but there is a problem with my screen, I think.
I can see your presentation, all right?
Yes, let me try to fix it. Okay.
Maybe you can switch off your camera.
Okay.
Good, very well. Try right now.
Okay. So, what about now?
Okay, I can see your presentation, all right?
For some reason, I can't go ahead. Let's try. What about this? I don't know.
Stamatis, if you're right with that, I can show you presentation and you can comment on that.
Okay, if you can
Sounds
go
good?
ahead. Okay.
No, I would need to be presenter though. So I will be presenter right now. And you should be able to see your presentation. Is it all right?
Yes.
Good. Let's see if it works.
Okay, let's start.
Good.
Okay, so one of the main INFRAMIX targets is to ensure the harmonious coexistence of all types of cars. In this direction, two important factors are, as you can see, user-centric design of transport and gradual and careful upgrade of the road infrastructure. The target is to meet the expectations of users from the start. So since we speak about interaction and user appreciation, let me start with the first poll. So can you see the screen now?
Not really, Stamatis, because I'm the presenter right now. So
Okay, what is the biggest expectation, please? Try this poll.
I can see some people are voting right now.
Okay, so it's okay. Yes, they're proceeding. Let's wait. They have been voted for half a minute till now. Okay, so please vote for your biggest expectation: traffic efficiency, safety, green environment, or the cost. Okay, I think I can close, and I will try to share the results. Can you see results now?
Stamatis, I think people can.
Sorry?
I think that the attendees are able to see the results if you want to comment on them.
Okay, so we see that safety got the highest score with 42%, followed by traffic efficiency. That is very interesting, and we comment on this and the INFRAMIX results later on. So let's go back to the presentation. It seems that safety is the most important factor. Please, can we go back to our presentation? Okay, thank you. So let's proceed with the next slide. Among the most important INFRAMIX objectives are to prove the added value of INFRAMIX developments to the daily lives of people, as well as to evaluate the user's acceptance of INFRAMIX development. So if we proceed, here is the methodology we followed. Two demonstration events were held in Girona and Graz, two workshops in Barcelona and Graz. We developed up to 11 research questions, 3 scenarios that you have already heard of them from the previous presentations, that were dynamic lane assignment, roadworks, bottlenecks, meaning on-ramps, lane drops, tunnels, etc. And we used digital questionnaires, paper questionnaires, videos, and we also evaluated the passengers' experience in demonstration. Please. Okay. And here you can see the 11 research questions I told you. that are divided on the left column into 3 users appreciation factors, meaning behavior change, as you can see on the left, willingness to use, perceived usability. Let's go to analyze them, please. Okay, the expected impacts that we want to evaluate are related to drivers, passengers, transport operators, and traffic conditions as well, and on traffic efficiency and safety. As you have already voted, these 2 factors, these 2, let's say, expected impacts of traffic are, as we know, the most important factor, traffic efficiency and safety. What was the methodology we used? We used the top 2 box, bottom 2 box methodology, focusing, as you see here on the right, on the strongest feelings. We evaluated the strongest feelings rather than the neutral ones. What means the top 2 box and bottom 2 box score? Top 2 box score is the sum of percentages for the top 2 highest points on satisfaction, appreciation, or awareness. On the other side, the bottom 2 box score is the sum of percentages for the top 2 lowest points on satisfaction, appreciation, or awareness. So we have either 2 positive or 2 negative results to evaluate. Let's proceed. Okay, how many people participated? The Spanish workshop in Barcelona, 40 people. Concerning the Spanish demonstration in Girona, we had 3 scenarios, were held in different days. 28 people participated in the first scenario, dynamic lane assignment, 20 people in the second one, roadworks, 21 people in the third one, that was bottlenecks. Concerning the Austria side, we had a workshop in Graz, 40 people participating there, and 20 people in Graz in demonstration live events. As an INFRAMIX, we always take care of having women represented in our project. So indicative percentage of women participants, it was in Spain demonstration, in Spanish demonstration, 31%, in Graz workshop 26. That is fair good if we consider the industry that is, let's say, traffic, with not so many women represented there. So let's proceed, please. The results. Yes. Okay. If you remember, the first research appreciation factor was the willingness to use. The actual question is if users state that are willing to use the information provided by ITS. In general, this research appreciation factor is increased with a real in daily life experience, something that, although not existing nowadays, obviously, at least to a great extent, it gathered high marks, high scores in our evaluation. You can see here in the middle, for instance, and concerning the Austrian demonstration site in Graz, that we reached up to 100%. That it's really impressive. Let's go on with the next appreciation factor, please, which is perceived usability, another important factor for user appreciations. So actually the question is, do the users believe that it will be useful? Why this factor is so important? Because although many innovations till now were seen by their inventors as useful in their minds, the users actually never welcomed them. So usability is a precondition for approval. And here, once again, I have an example, again from Austria, Austrian workshop, again with some really very good results, from 92 to 100%. Let's proceed with the behavior change. Probably the most important appreciation factor. So, do the users state that they would consider following the suggestion provided by intelligent transport capability? Why I said that it is most probably the most important appreciation factor, because in comparison to willingness to use that we saw 2 slides before, it's a step forward because it is related to the change of driving process, of our habits and driving style. Here, once again, although we don't have the 100%, we had in other appreciation factors. Once again, in a Spanish workshop, as an example, the results are very, very promising, reaching up to 97%. Thank you, Anarita. Let's proceed. Okay, and here are some overall results. Beginning, I have included here all the 4 events, the 2 workshops in Spain and the 2, the workshop and demonstration in Spain and the workshop and demonstration in Austria. So here are the results. You see the mean value and the standard deviation here instead of the top 2 or bottom 2 box methodologies here. So you see here some results. For instance, I have put in yellow color what we regarded as very important to follow suggestions, meaning that you are, let's say, very willing to change your driving behavior. And you see 480, 428, 40, 50, 425 out of 50, out of 5, sorry, that is very impressive results. Concerning your first poll answers, if we go to the bottom, we have in green color traffic safety and traffic efficiency, traffic flow, in other words, that you voted for the most important expected impacts. And then the results are quite promising and optimistic, reaching up to 4.40. Let's proceed. So more or less the same results are in other 3 events. Here we see Spanish demonstration, and then in green you had these numbers. That's in scaling of 5. We have 395, 425, etc. And at the same time, for the behavior change, again we have some very good results. And we can proceed with Austria. Thank you. Austria workshop. Again, very good results. In Graz, you see, and not only the yellow and green color, you can see also the other results with, if you permit me, one slight exception. You can notice in the gray area of my table that is named expected impacts results, that is scaled from 0 to 10. You see that the results, let's say, are not so bad anyway, but are not so impressive. What does it mean? That as far as the expected impacts, not on the broader categories of traffic efficiency and safety that are on the bottom, but on specific traffic conditions, the results, let's say, are not so impressive, although are very good, gathering marks and scores over 7. But let's say people want to see something in their real lives. Let's proceed, please. Anarita, can we proceed? Here are the conclusions. So, willingness to use, perceived usability, and behavior change, the last one very important, were evaluated, and they were evaluated with an acceptance over 70%. That is really promising. Drivers, passengers, and road operators believe that the advanced ITS functionalities will bring positive change in traffic conditions, especially in safety and efficiency. but they are unsure about the specific characteristics of this improvement. So we are talking about a promising and optimistic results, but we need a gradual upgrade of intelligent systems infrastructure so as to have everyone satisfied. I'll finish my presentation with the last one, Paul. So the next one. Okay, here we are. Can you see the questions, Anarita, please?
Stamatis, I see the same thing that you are seeing. So
Okay.
I can see the poll is in progress.
Okay.
So
So what is your
participants,
biggest
please
fear
vote.
in using advanced traffic management features in the future? Not confident about the benefits. I'm afraid to use them if I don't see the results. I'm afraid it will be difficult to understand and use them. Okay. Here we have, let's try. We had a consensus of 100, but the results are getting more mixed. Okay. Let's vote. Let's wait. Okay. Okay. Let me share screen. So the biggest fear is I'm afraid to use them if I don't see the results after, and then about the impact. So since if we can go back to my presentation, please.
Coming.
About, thank you, some slides, one slide before, please. Okay. So people want to see the results also in their real lives. That makes us think that one of our biggest obligations is that we have to implement a gradual upgrade of intelligence system so as everything be satisfying at the end. People are optimistic. People, they think that traffic safety and efficiency will be improved, but actually they want to see something more clear in their real lives. That's all from me, and I'm open to questions. Martin?
Yes, thank you very much, Stamatis. I would like to ask one question, and the question is, which stakeholders participated in the user appreciation events?
Excuse me, can you repeat, please? Because it was a disconnection. Martin?
Yes, the question is, which stakeholders participated in the users appreciation events?
Okay, so if we, Anna-Rita, can we go back to my presentation, if it is possible?
Yes, please give me 2 seconds.
Thank you.
Is there a specific slide you want to share?
Yes, it is the 9, but anyway, if it is difficult, I can answer about the stakeholders. Leave it, Anna-Rita. So yes, we covered, I think, all the stakeholders. It's okay, Anna-Rita, it's okay. We covered every category of stakeholders of ITS. So there were industry, road operators, there were consultants, research institutes, infrastructure, vehicle manufacturers. So I think that all the stakeholders were participated in the 4 events. And I think that the sample we used, it was quite representative of what we wanted to evaluate. Thank you.
Okay, thank you. Then I would hand over back to Anna-Rita.
Okay, thank you, Stamatis and Martin. I would like to share my screen right now. Good, very well. So you should be able to see my screen. Okay. Yes, here we are again. So let me introduce myself once more. I'm Anarita Meserri. I'm Communication and Dissemination Manager at UNIDE. We're based in Barcelona, Spain. And what I would like to do with you today is give a brief introduction on the INFRAMIX roadmap that we've been developing during the project. So here we are. Okay, I would like to cover 4 main points with you today. First of all, the challenges that we met.
Sorry, Anarita, but we cannot see your screen right now.
What about now?
No, it works.
Good, very well. Thank you for telling me. So I would like to cover 4 points with you today. First of all, the challenges that we met in INFRAMIX, and then the solutions that we came up with to meet these challenges. Then we will briefly go through some guidelines that we developed to implement these solutions. And then finally, a timeline for actual and feasible implementation of these solutions. Good. So as Martin explained earlier this morning, we focused on 3 main traffic scenarios that were the main INFRAMIX challenges. And we took these 3 traffic scenarios as starting point for developing solutions and outcomes. So what are our solutions? We've been through them throughout the webinar, but I would like to quickly recap them with you right now. So first of all, traffic management measures. And as we said already, they include traffic management strategies, traffic control strategies, but also control and estimation algorithms. Then bidirectional communication, vehicle to infrastructure, and the other way around, infrastructure to vehicle. And these includes transport messaging protocols, for example, but also routers for autonomous driving and enhancement of cooperative ITS G5 communication. Then we have digital infrastructure, so sensor technologies, roadside units, and so on. And then physical infrastructure, so for example, new segregation elements, new visual signs, as those that are visible on the IP7 in Girona, Spain. Infrastructure classification scheme, so all the asset classes that we've been through this morning. And then simulations and safety performance criteria. This solution includes microscopic simulation, submicroscopic simulation, the co-simulation framework, but also a new set of safety performance criteria that we look at during the project. Then hybrid testing, so Celine before me explained all the features of this solution. And then just before me, Stamatis went through use cases and evaluation methodologies. And then this present roadmap, that is a set of guidelines to actually implement all the solutions and outcomes. So a question here that might arise is, how are our solutions making a difference in the daily life of stakeholders involved in the connected and automated driving? Well, let's go through it. We identified 5 main stakeholders, being industry, infrastructure operators, policymakers, researchers, and key influencers being, for example, standardization body at the European level and beyond. And also the general public, so every potential driver in Europe, and also every lay person that's interested in our work. So we hope that all our solutions will help industry, for example, to provide more efficient, more innovative products, and infrastructure operators to provide better, more efficient service. Also, we would like to help policymakers to take more informed and decisions and investments as well. And we hope that researchers could continue their work and build on INFRAMIX solutions and results and outcomes, and also the general public. Well, at the end of the day, we all hope and work to have a more efficient, safer, and greener transport on our roads and highways. Very well, so here's a set of guidelines that we developed. So a set of concrete actions that are needed from all the stakeholders that we went through before. I can't really go into detail right now, but please be aware that this document, this presentation will be available after the event, and also this document will be publicly available as a INFRAMIX deliverable at the end of the project. And of course, INFRAMIX partners are expected to perform a leading role towards other similar stakeholders. So we would like to be pioneers and open the way towards the implementation of our solutions. Okay, let's go quickly through this roadmap. We started to think about the future of our solutions, right? So we envisioned a timeline of 10 years time, starting from now, starting from year 1, meaning the end of the INFRAMIX project, and extending until 2030, more or less. So here's a set of actions that are needed, activities that are needed starting from the end of the project. First of all, we would like our solutions to be adopted, of course, because new concepts and notions developed by INFRAMIX, such as, for example, the ISA classes or the 3 traffic scenarios, they've been well received at the international level, but they also need to be widely acknowledged and adopted by relevant stakeholders, so to allow all the actions and activities that follow, so integration, standardization. But let's go through them. So integration of technology, what does it mean? We expect at least in the 2 years to come, the INFRAMIX solutions and outcomes to integrate with the existing technology, and also with other technology, ensuring security, cybersecurity, but also a stronger mobile network, for example, so the 5G technologies. And then after that, we expect a period of standardization and policymaking, meaning that the INFRAMIX solutions need to reach and be accepted by the European and international stakeholders and standardization bodies. This means that we can allow them to reach a wider diffusion, acceptance, but also to be interoperable with other results. And then policy making, we need to develop awareness among these stakeholders in order for them to adopt these concepts and integrate them with technologies and standards. Then after that, starting from year 5 more or less, so meaning the mid-20s, we expect a period of implementation, starting with tests, and then demonstrations, and then the actual deployment. So first of all, we need our solutions to be tested in different countries and scenarios. And then we will need a period of demonstration, meaning of smooth running with no modifications until the actual deployment. And then the deployment means the real actual implementation in real life settings. All these activities that we've been through need to be implemented in a framework of awareness and coordination. This means that starting from right now until at least the 10 years to come, we need to develop awareness of the solutions. We need the European stakeholders to know our solutions, to know our results. And also, this could accelerate and facilitate other activities, also by other similar initiatives and projects. So that's why we need to cooperate, because we need to identify the complementarities, but also the differences, the peculiarities of each initiative, of each project. And this will also increase the possibility of merging the efforts by similar European projects. Very well, so that's the end of my presentation. Let's go quickly through what I presented today. So first of all, we identified the 3 traffic scenarios as the main challenges of INFRAMIX. Out of these challenges, we developed 9 solutions that are actually meeting the stakeholders' needs. We also introduced a set of guidelines, meaning the set of concrete actions that are needed from all involved stakeholders, and then a timeline of feasible implementation that will run starting from now, from the 10 years to come, at least. So that's the very end of my presentation. Here's my contact in case you wanna forward me some requests or questions. Again, please be aware that all these presentations will be available after the event. And now I would like to introduce the next speakers. Okay, here we go. Very well. So I would now leave the floor to my colleagues, Yannick Wiener. Again, you met him during the morning. He's project manager at ASFINAG. And then Stefan Duhl, he's development engineer at BMW. And also Marco Rosenmüller, he's research engineer at TomTom. So thank you guys for being here again. I can see your screen and camera. So whenever you're ready, the floor is yours. I can't hear you, Yannick. I can see you're speaking, but I can't hear you.
That's true. I was muted as hard switch. Thanks. So I won't introduce myself once more, I guess, but maybe Marco wants to introduce himself.
Yeah, so I'm research engineer at TomTom, and yeah, I will give you just a brief overview of TomTom's perspective as a service provider on the INFRAMIX measures.
Okay, thanks. So then now I am. I'm sharing the right screen now. So. Okay, I think everything is fine if I can see it correctly, right?
Yeah, yes, I can see your screen correctly. Thank you.
Yeah. Okay. So in this slot, I wanted to give you an road operators and service providers view on the INFRAMIX measures, on the INFRAMIX results. And I will head off right where we left actually in the morning session. So just have have a look on these ISAT classes that we've covered several times already, but how were they received in and outside of the project? And there are just several statements that got in that should be at least mentioned here. So first of all, it's the infrastructure classification scheme can really facilitate the transition period. This is what people think involved in the project and also outside of the project. And this is also the core part of ISAT classes actually, and it should be able to ensure safety and security during this transition to a mixed traffic environment. Also, the classification helps to understand the capabilities of the infrastructure, but there is also some criticism on the ISAT scheme, some valid criticism actually. For example, of course, it's always a bit difficult when you try to map quite a complicated concept to such a list, basically. And criticism, for example, by OEMs is that it may be a bit difficult to interpret. But also keep in mind that it's not yet written in stone, this scheme. But all in all, it was received very positively, especially also in the road operators community. But just also wanted to mention this. There is, of course, also criticism about the ISAT classification scheme. Then just an experiment here. You just voted some 2 or 3 slots ago. You just voted on what is the biggest expectation from the intelligent transport capabilities. This was the the results on that. So it's safety and traffic efficiency were the results. So let's have a look. What about this here? I brought you some accident statistics from the Austrian road network. So keep in mind it's the highway network we're talking about, because ASFINAG is a highway operator, but still. So these are accident numbers and accident statistics from 2018. And yeah, what kind of potential of the INFRAMIX messages can we draw from what we see here? So maybe let's just have a look here. It's more than 40% of all the accidents in the past years were one of those three categories here. It was inattentiveness, distraction, or insufficient safety distance, or inadequate choice of speed, or similar things. And yeah, so this is something that of course can be tackled by CITS technology. And if you have on the right hand side here, if you have a look on what kind of accidents resulted from this, it's well, of course, something like a solo accident. The first category here is something that can rather not be addressed by CITS, but those rear end collisions that we have here that make up for about 40% and even 50% in roadwork zones. This is, for example, something where we see great potential, and especially as we see here roadwork zones. Well, no, we don't see that roadwork zones are slightly more dangerous. This is something that I have to tell you, because roadwork zones are responsible for about 6% of the accidents on the highways, but they only make up on average for 3% of the network. So more or less you can say they are double as dangerous. Yeah. I'm trying to switch to the next. Now it's working. Okay. And yeah, roadwork zones are a bit more dangerous than the rest. And what we experience as a road operator, this is a number that highlights this problem quite well, is that we lose 5 to 10% of roadwork warning trailers. Those are those kind of trailers that are just at the start of roadworks, warning about roadworks, and we lose 5 to 10%. Just think about this number for a second. This is a lot. And also in Germany, as far as I know, it's the same. This means this is one trailer every 2 weeks in Germany or something, I guess. So, yeah, this makes up for quite a number of accidents, and yeah, and also of course has some costs of a road operator is related to those kind of accidents. And here we see great potential in CITS warning. For example, the denim message, for those who are familiar with CITS, is classically warning message for this. In the future, we would like to have roadwork trailers who will be able to send out this message via, for example, ITS G5 warning incoming vehicles. Okay, and now I will hand over to Marco for the next 2 slides. Marco?
Yeah, thanks, Yannick. So as mentioned, just a brief overview of TomTom's perspective. So TomTom is a service provider, so we are providing map data, we are providing traffic information for navigation systems integrated into the car, and we're also providing HD maps for autonomous vehicles. And so regarding INFRAMIX, I want to split into autonomous vehicles on the one hand and conventional vehicles, because we're talking about mixed traffic, right? So we want to reach all the vehicles on the streets. And yeah, from a service provider point of view, there are different ways of communicating information about roadworks, for example, to the cars. And in INFRAMIX, we analyze different communication channels, such as ITS G5 and cellular communication, as we've seen in the morning. And based on these communication channels, so for example, if you have cellular communication, there can be different protocols used. And for example, there is the TPEG protocol, the TPEG standard that is used already nowadays to communicate such messages, and in the future that could be even extended for messages that are more related than to the INFRAMIX scenario. yeah, in addition, then also the HD map plays a crucial role for autonomous driving. So actually, it's enabling autonomous driving, right? And without an HD map, there is currently no autonomous driving possible. And that also means that, for example, in a roadwork situation, you need all the detailed information on top of the HD map, the dynamic information about roadworks, for example, that provides the detailed geometry to the car such that the car can stay in autonomous driving mode in the future. Otherwise, it would need to switch to manual driving mode. And yeah, that's then finally also another communication channel, how such messages can be communicated to the car, which means the dynamic data is already integrated into the map. And that's also what we see at the moment. So in current TomTom maps for navigation systems, for normal navigation systems, their long-term roadworks, for example, are already integrated into the map, and with an increasing map update frequency. So if the maps really update in short intervals, then also more dynamic information can be integrated into the maps. And for autonomous cars, that means that the maps that are streamed, for example, there is a TomTom Auto Stream product, that those map data does already include dynamic information. And this dynamic information then, once it is in the car, is then handed over to the autonomous driving system via Vehicle Horizon that we looked also at into in INFRAMIX. There are existing protocols such as ADASIS, and in version 3 of the protocol, you can have lane level precision information and high precision information that is then really needed for the autonomous vehicle to actually drive in such situations. And on top of course, roadworks, there then can be additional types of information that we have analyzed in INFRAMIX. So we also looked into conventional vehicles. Can I get the next slide, Yannick?
Yeah, it takes some time for me to switch. Okay, now.
Thank you. Yeah, so we also want to reach non-automated drivers, at least in the beginning, right? And there we looked into what is possible. What could you give to a human driver to give you all the information that he needs to follow the control to increase traffic flow, for example. And there it became clear that so on the one hand you need detailed lane guidance. So that's something you see here on the left side. So that's a view of TomTom navigation app, where you have the different lanes visualized. That's already part of the current product. But here we just overlaid additional information from the INFRAMIX project, for example, different speed limits on the different lanes. So that's all good and fine, but for a human driver that is driving on the street, that gets very quickly too much information. So the human driver is then overloaded with all the information. And what you actually need is then customized visualization mechanisms to actually really tell the driver what he needs to do, because just visualizing what is happening on the different lanes is just too much information for the driver. A bit of a problem here is conventional cars that do not have any sensors where the car is able to see on which lane it is. So in this case, as you have seen here in the screenshot as well, you don't know where the car is because this is just running on a phone in this case, but it could also be integrated in the car and then you would have that information. But if you don't have that information, you cannot do a lot, right? So then it's getting difficult, but if you have that information, then you can provide advanced visualization methods to really guide the user, for example, to use a different lane. What became also clear in the analysis is that some types of advice are, of course, not really useful for human drivers. So they're really geared towards more automation. So for example, time gap advice, so that it's clear that a human driver cannot keep up with a car in front of him with a certain distance and time. So that's just not possible. So they really need automation within ACC. Yeah, and given that, then there's quite some opportunities to integrate the information that comes from the INFRAMIX project into the different types of the cars. And yeah, with that, I want to give back to Yannick then.
Yeah, thanks. If you remember, the second point in the poll that I showed you was about traffic control strategies. So what I brought you here is a short video short animation of such a possible control strategy. So when cars and also automated vehicles are approaching such, as we've seen before, such a roadwork zone, then of course there should be, since it's a lane drop ahead, there should be some control strategies telling the cars what to do. And INFRAMIX also looked into that, and we heard about this already in the morning session about different kind of control strategies. And of course, this is something very important for road operators. And control strategies and also some possible recommendation and commands made also a huge part in INFRAMIX. And there are different kinds of such control strategies. And from a road operators and also OEM view, we did some brainstorming on what worked fine and what we could recommend and what we don't recommend so much. So, and we summed it up in this slide here. So if you see if speed limits is something that everybody can relate to, is something common, and it works fine. But we've seen this, the distance gap controller would even work better. We are not quite sure about the safety issue. As far as we see, there are not really some safety issues about the distance gap controller. Of course, keep in mind such control strategies always it's the necessity for them to condense the traffic into more traffic into the same space. That means if you have, for example, car distances or time to collision for the experts as a key parameter, yeah, then this will go down a bit, but still in our project, this didn't show really dramatic numbers. So I think the distance gap controller is something that we should definitely look into when automatic vehicles will come to our roads. As far as the acceleration advice is concerned, there was the idea to give additionally to a distance gap advice and acceleration. This works fine, but actually, as far as we saw from the road operator's perspective in INFRAMIX, the distance gap controller works fine as it is. So, and there's very little additional effect of the acceleration. There is additional effect, but it's I think we would stick with the simpler one that already works fine. The lane change was a bit inconclusive. Also in simulation results would be the advice to change lane, for example, at bottlenecks. I think we should maybe in following projects look rather into a keep to lane advice. It would be interesting to have automated vehicles, maybe give automated vehicles the advice, you keep to the lane and have other vehicles change the lane. I don't know, could be a possibility. Then there was the dedicated lane. Dedicated lane was one of the use cases in INFRAMIX, which, yeah, we were, from the results, to be honest, not so fond of, because first of all, we've seen that there are benefits for the automated vehicles. Yes, that's true. If you close off a dedicated lane for them, but you cause congestions for the other lanes, for the non-automated vehicles, and no matter what, that's what the simulations told us. So from a road operator's view, we would rather not pursue this this control strategy, actually, because it doesn't really show any benefit for us. Also, the safety parameters went down. So neither of those key performance indicators really is supporting to pursue with a dedicated lane for automatic vehicles for us. The roadwork zone, I've discussed this already. There is really high safety potential in this one. So concerning the traffic control strategies, we saw that if you do not apply traffic control strategies, especially when more and more automated vehicles come to the road, then we will run into problems, because there will be more congestions but only if you don't have any control strategies. And INFRAMIX pointed out new possible control strategies that counteract these effects and that seem to work fine in simulations. And we also learned that CITS is a major factor in those strategies. And something that's very important for ASFINAG as a road operator is that well, those roadside units, this is a Wi-Fi technology as far as ASFINAG is rolling it out at the moment for short range. But either technology in the short range has the problem that's a short range technology and that you don't have, the question is always, do you need to have a full coverage or not? And the simulation told us, no, you don't need full coverage. It's enough. Results are good enough if you have those roadside units positioned at strategic points along the road. And this is a very important finding for us because, yeah, it's roadside equipment. It's something that the infrastructure has to come up with. So out of curiosity, I have a short poll for you. So after all of what you've been hearing so far about the CITS services, when do you think you will start using it as a road user, mainly as a road user? How long will this take? Will this be rather soon in the next 5 years? Are you already using it? Could be, or will this take even longer until the 2030s or even never? So I think people are still voting. Let's see, nothing changes. So I'll close it in 3, 2, 1. Okay. So most of you think that they will start using it, well, in the next, let's say in the next 5 to 10 years. So yeah, maybe depends on when you are planning to buy a new car, but actually you're quite optimistic on it if I see it correctly, because basically within the next 10 years, all of you are expecting to be using CITS technology. That's an interesting outcome of this poll. So what about the road operators? So here I have a statement from the other road operator in the INFRAMIX consortium. That's Abertis Autopistas from Spain. So they are planning to continue exploring the INFRAMIX results and to do further tests on cross-border traffic strategies and further test different communication technologies. And they do not take a position on a specific communication technology so far. They want to do some further testing and study further the technical aspects and the future role of the road operator. In Austria, we are actually, so coming back to the poll question that I was just asking, we are using CITS already in a pre-deployment, and we are rolling out, well, we have a running tender. We are rolling out this year and next year, actually, so with the productive service. We support a hybrid infrastructure. That means we are rolling out an ITSG5. This is the short range technology. That is something that we are rolling out as roadside units on the road. But we are also supporting the cellular way, the long range way, because we just think they complement each other. And you have different use cases where one makes sense and where the other makes sense. So for example, the Roadworks trailer that I've showed you before, this is something time critical. This is a typical short range use case, where other use cases that might be data intensive or something like this might favor the 3, 4G or maybe in the future also 5G way. But both of those will be available on the ASFINAG network. As for the pilots, so we tried with 25 roadside units already some 5 years ago. Then we have 25 operational in different pilot sites right now as we're speaking. And as I said, we are rolling out this year, next year, 175 in strategic areas, strategic corridors, and there are more to come after that. And yeah, well, INFRAMIX really showed that our strategy here works. Our strategy is fine, that we are on the right way as a road operator here. So yeah, I've showed you some, well, okay, let's just comment on this one. These are some of the typical services that will be available starting next year on the ASFINAG network. These are classical warnings, warning from a broken down vehicle, a roadworks warning, or the classical speed limit. I will not comment on all those day 2 use cases that are farther in the future due to the running time, I guess. And yeah, to close off the demonstration, I brought you 2 videos from the demonstrations. So we have a demonstration here in Austria, where we demonstrated that we are able to send and receive such CITS messages in the INFRAMIX project here in a test vehicle in a test environment. That worked quite fine, and you saw the passenger screen here. And also our colleagues in Spain, Otto Abertis, with other INFRAMIX partners, of course, did some tests mainly on the dedicated lane. Okay, there is some, okay. And there is the full video is available in the download section. As far as I know, it's just a teaser that I'll give you here, that you get some impressions on how this video looks like, and maybe you can have a look afterwards. Okay, so that's it from my side.
Yeah, thank you, Yannick. Thank you, Marco. I would just ask one question, since we are already over time, to both of you. So the question is, from a road operators or service providers point of view, what should be the focus of future similar projects or potential follow-up projects of INFRAMIX?
Mm-hmm. Should I comment, or do you want, Marco? Or I can say something about. Yeah. Yeah, as you've seen from my presentation, I would say that we definitely have to look into traffic control strategies, because this is something that, well, one key result of the INFRAMIX project, that traffic control strategies will be necessary when automated vehicles reach the road. We have lots of potential due to the amount of connected vehicles also that will be there. But so first of all, when the first automated vehicles reach our road, they will be a bit of an obstacle, actually, because people won't be used to coexist with them on the road. So yeah, this is something we need, and this is something that only can be addressed by simulations so far, because at the moment we have very few connected and no automated vehicles on the road. So yeah.
So maybe from my point of view, so it could be also, yeah, there's, I think, quite some open questions regarding the integration of really dynamic data in HD maps, so that really the up-to-date, really short-term information is available to the autonomous cars. So that could be some focus as well.
Okay, thank you, Marco. Thank you, Yannick. And I will hand over back to Anna-Rita.
Thank you, everybody, for your presentation and answers. I would like right now to change presenter, and it is a pleasure for me to introduce Tom Alkin from the European Commission. So Tom, thank you for being here. It's a pleasure for us to have you with us and to hear your presentation. So whenever you're ready, the floor is yours. Tom, I'm not really sure whether you're speaking or not. I can't hear anything, but I can see your screen. I can see there's a sound problem here. Let me check.
Yes, I think I'm unmuted now. I was not able
Okay,
to
very well.
unmute myself. Can you all hear me well at the moment?
Yes, I can hear you. And I can see your
Okay.
presentation all right.
Excellent. So thank you all. It's been a long day, so it's good that you are hanging on till the end. It is an honor to be invited to this final event, although unfortunately there's no traveling and we cannot see each other in person. Hopefully these times will change soon. First of all, I would like to congratulate you all with the results of the INFRAMIX project. Pretty impressive results over the past 3 years. And I'll give you a short introduction of myself. For those of you who don't know me, before coming to the Commission about a year and a half ago, I was working at Rijkswaterstaat in the Netherlands. Rijkswaterstaat is a difficult Dutch word for the national road operator. And there I had quite some experience from the road operator's perspective in connected and automated driving. So a year and a half ago, I joined DG Research and Innovation, and together with my colleagues Lutger Rogge and Susanne Kraak, we are responsible for connected and automated mobility in research and innovation. So I have a couple of slides that I would like to share with you. So we are approaching the end of the current framework, and as you can see, in Horizon 2020, we had allocated approximately 300 million euro for calls on automated road transport. And you see here a list of the different elements that we focused on, ranging from large-scale demos to safety, road infrastructure to support automation. That's what we are talking about today, of course. But INFRAMIX is also linked to safety and user acceptance and traffic management solutions, I think. Connectivity for automation, testing and validation procedures, which is also quite a challenge. The assessment of impacts, benefits, and cost of these systems, support for cooperation and networking activities, and last but not least, I would say human-centered design of automated vehicles. Let's see, go to the next one. So here's quite an overview of projects in the past, and some of them are still ongoing. And you see here that INFRAMIX is also mapped on this view. You see it is coming to the end, and there are several other projects that were dealing with the relation with infrastructure. As this morning was mentioned by Martin Rus at the beginning of INFRAMIX, most of us were a bit more positive than we are now. I wouldn't say that we are negative now, but maybe we are more realistic. We have seen over the past few years that it is quite complex to develop connected and automated mobility, and especially have it applied in practice. So most of you are probably familiar with the Gartner hype cycles. I've looked them up for the past 10 years, I won't show every graph of every year to you because of the limited time, but I encourage you to look them up. It's interesting to see how the topic of autonomous vehicles goes over this graph. And in 2010, it was the first time you could see it on the graph. It was expected to take more than 10 years to reach productivity, the plateau of productivity. And 6 years later, in 2016, I think we were at the peak of automated vehicles. There were a lot of interesting announcements by companies at conferences as well. A lot of promising ideas and very ambitious projects. And as you can see here in this graph, it was for the first time that autonomous vehicles went slightly over the top. If you look at the version from 2015, it was right at the top, and it was only expected to last 5 to 10 years for automated vehicles to come to the roads. And now you see that this was the first time that a little bit more realism was settling in. And what you could also see if you fast forward to the most recent version, this is of last year. Actually, 1 year before, it was the first time that Gartner decided to make a split between autonomous level 5 and autonomous level 4. Of course, we all know that there are even more distinctions, and you shouldn't call an automated vehicle of lower levels an autonomous vehicle. But anyway, I think it is good that some distinction was made here to show that there are different developments going on. Also, one of the things that happened in the Commission over the past year is last year in summer, we organized the single EU-wide platform for connected, cooperative, and automated mobility. The idea is that we have one platform in Europe to discuss and address a lot of issues that are multidisciplinary in nature. Many various stakeholders are working on this topic, and also we need to develop an EU agenda for testing and better coordinate the research and the pre-deployment activities. We should also agree on common evaluation methodologies. We should facilitate access and exchange of test data. And assist the Commission in thematic areas. And one of those areas is related to INFRAMIX, I would say, is the road transport infrastructure and the digital infrastructure. And many of you, I guess, are familiar with the several working groups that we have in this platform. I am myself the chair of Working Group 2, Coordination and Cooperation of Research and Innovation and Testing Activities, where three main elements that we are working on is a European knowledge base, a European common evaluation methodology, and a framework for test data exchange and lessons learned. The working group that is most related to the INFRAMIX work is the physical and digital road infrastructure. As you may know, the working group 1 is coming to an end this summer because although it is very important to develop an EU agenda for testing, this will now be taken over by the European Partnership under the Horizon Europe program. So this is the next framework program that will start next year in January 2021. And the idea is there to establish European leadership in safe and sustainable road transport through automation by having this partnership established with different stakeholders, where the vision is that by combining connectivity, cooperative systems, and automation, we will be closer to Vision Zero. Vision Zero here means, of course, is related to safety. But the goal is not only to increase safety, also to reduce congestion, contribute to decarbonization, have more inclusive mobility as well. It basically means that we can expect to have societal benefits of CCAM if it is done right. It's easy to say if it's done right, but what does that actually mean? And what does it mean in practice? And I think that's why we need a lot of research still and cooperation. So a few more words on the higher level vision and expected impacts. So these are the potential impacts that we can have if CCAM is done right. And I would also like to emphasize that it doesn't mean necessarily that connected and automated vehicles are the answer for all your mobility problems, especially if we look nowadays in these challenging COVID times. You see that especially active mobility as cycling and walking are very important, especially in urban areas. And of course, coming from the Netherlands, I can only applaud that cycling is being taken up. But I would like to mention that you need a smart integration in the whole mobility ecosystem. And if then the smart choice is to use a car, whether it is a private car or a shared car, it might as well be connected and automated. So that would be the premise, and not to have as many connected and automated vehicles as possible to solve all your problems. The partnership focuses on 7 different clusters. You can see them here. I would also like to mention to you that you can still join as a stakeholder. I guess, Martin, you are familiar with this. You may even have discussed it already with the project, because I think INFRAMIX can really contribute to this partnership, and especially in cluster number 4. There you see it is called Integrating the Vehicle in the Transport System, where some of the topics are on remote operation and surveillance, physical and digital infrastructure, connectivity and cooperative systems, and also fleet and mixed traffic management. So these are most closely related to the INFRAMIX topics. If I look at, I don't have a slide on that, but I can tell you a bit more on the next steps for the partnership, because there are some stakeholder meetings. They were held last week. But there is a second round of stakeholder meetings on June 16th, 17th, and 18th. And the stakeholder meeting for cluster number 4 will be on June 17th from 4 till 6. If you want to register, you can email to info@ertrac.org, or you can ask Martin Rus, because I'm sure he can coordinate this all. Okay, then maybe one of the reasons I was asked today to join the meeting and also give a presentation is because of this picture. I'm happy to see that it is being used. That means that the idea I had about two and a half years ago about visualization of the operational design domain is useful. I first tried to do it in a 3-dimensional form, but that became really too complex because you would need 3 axes for all conditions, always the time elements, and everywhere the geographical elements. That's too complex for starters, so that's why I decided to do it like this. And you can use this for every level of automation. Of course, for level 5, you will not have a rectangle. Then all the space is used or useful for the vehicle. Of course, you have seen that this is the theoretic representation, and this is the more realistic representation. And you can see that the three most common reasons for having gaps in the operational design domain are related to the infrastructure, the amount of traffic and traffic behavior, and the adverse weather conditions. So that led me to think that it is very useful to talk about the ISAT levels, but we have to be quite nuanced about this. It's very good to have this, and now I see that something strange happened with this this picture, by the way. It is somehow upside down, but you have it in several presentations in the right form. One thing that we have to keep in mind is that if, okay, first of all, there is no direct correlation between the level of automation of a vehicle and the ISAT level of the road. And even if that would be, so let's say, for instance, a level 4 vehicle would be able to drive on a level B road, then that combination can never be guaranteed to always allow this operation, because there are more factors that contribute to having gaps in the operational design domain that are beyond the control of road operators or the capabilities of the technology that is being used by the OEMs in the vehicle, so to say. The other thing that we should keep in mind is that for both the SAE levels of automation and I think for the ISAT levels describing the functionality of the infrastructure related to automation need more functional detailing. Because one of the famous examples is that people often talk about a level 4 vehicle, but it can be both a shuttle in a dedicated area or a person vehicle on the highway. And those are two completely different functionalities, two completely different vehicles with completely different approaches. But they can be called the same. So in practice, you really need more detailing to bring those two together. Having said that, I think it's a good approach to try and combine this in an attempt to have a methodology to start describing ODDs and relating it to the capabilities of the vehicles and its surroundings. And it also may be useful to use this, for instance, in the type approval approaches, where you can maybe start testing vehicles on their capabilities in a certain operational design domain and not test it for all possible situations as a start. I see that I am approaching the end of the time that was allowed for me in the agenda. So I have also reached my last slide. It's quite difficult to do a presentation without the interaction of the audience, but we have some time for questions right now, if I'm correct. Thank you for your attention.
Thank you very much, Tom, for your presentation. It's an honor for us that you have presented the European view and shared several insights with us. And I would like to ask the following question. So how can the uncertainties related to the future development of, for example, vehicle technology can be considered or tackled? Yeah.
Okay, I understand the question. I'm not sure if I have an answer to that. To give you an example, we are now all assuming that connected and automated vehicles will use vision for their positioning on the roads. They all use cameras in one way or another. So the let's say the lane markings are deemed to be essential for exact positioning on the roads. Of course, there can be different technical solutions to that. In the past, we have seen approaches where magnets were being used in the roads. That would be a drastic change. But we also have to keep in mind that even if such a potential, let's say, shift of using technology could lead to a potential shift of infrastructure requirements, you still have to design and build for both the automated and non-automated vehicles on the road. So as long as you have mixed traffic, in the example that I just described, you could not take away the lane markings because you still have to cater for the non-automated vehicles. You could, however, have magnets in the road in addition to maybe enhance the performance of the automated vehicles. I think one of the most important things to deal with these kind of changes or progression is to have multi-stakeholder cooperation. So I would really call upon all the stakeholders to join the European partnership and share as much as possible.
Mm-hmm. Thank you very much. And another question from my point I would like to ask is what, or just 1 minute, I'm sorry, I guess I have missed one. The following question: how important is, in your opinion, the digital infrastructure for level 4/5 driving on all areas?
I think it's very important. Also, here by saying level 4/5, that's something we should stop doing because there's a big difference between it. And within 4, I mean, you could have, if you have some shuttles in a limited dedicated area, the importance of a digital infrastructure could be less of importance than in other conditions. So it's really important to try and be more specific in terms of functionality to see what needs to be done and what is necessary. But having said that, I think that the digital infrastructure is really important. I would say all possible technologies and infrastructures that can improve the performance are at this time needed.
Thank you. And then I have another question which was asked, and it's the following. Good view of lane marking issue regarding mixed traffic. In terms of road markings, not using magnets, what is your opinion on the lower levels of retroreflection, millicandelars?
Okay, that's a quite detailed question. I would say it depends on the capabilities of the automated vehicles, whether the quality of the lane marking is good enough. Of course, if it is good enough for humans, it should be good enough for automated vehicles. But we have seen in practice, and I know that there are some tests that were done also in the Netherlands last year, where they drove around under different conditions, and there's a big variance in the let's say in the weather conditions. So describing the requirement in this way may not always guarantee the desired outcome. So with the sun very low and the lane markings wet, that could lead to problems.
Mm-hmm.
I hope this answers the question.
Thank you very much. Then I would like to ask one last question. Yes, it says I have received a thank you as well. Then I would like to ask a last question. You already mentioned the COVID topic, and the question is, what do you think, from your point of view, would be the impact of COVID and on connected and automated driving? Is there any, or yeah?
Yeah, that's quite difficult to answer, and of course I can speculate on that, and that is what we all have been doing for the past 3 months. So it's interesting to go back 3 months ago and ask yourself how you were looking at the COVID situation. Is probably not the same as you did 2 weeks ago or today. So a lot of speculation there. One thing could be that, well, if you have taxis or shuttles or vehicles that do not need an operator anymore, that would be helpful with social distancing. But as I also mentioned, vehicles may not necessarily be the dominant form of mobility, especially in urban areas anymore, where we may need to have more space dedicated for active modes of transportation. Another impact that's difficult to assess for me is whether, I mean, most of the OEMs really have a hard time in terms of production, and this could have an impact on the budget for R&I, which could also have an impact on the development of connected and automated vehicles. So these are the things that I could speculate on.
Okay, so thank you very much again, and I would then thank you, and I would then hand over to Anna-Rita again.
Here I am. So many thanks. It was a very interesting presentation and also question answer time. So thank you for that, Tom. And now I would like to introduce again Martin Ross from AustriaTech, Managing Director AustriaTech. Martin was with us at the very beginning of our webinar. So let me change the presenter again. Okay, Martin, now you have the floor whenever you're ready.
Yes.
Thank you.
Yes, thank you. So I will give you my presentation, hopefully the right one. Oh, you should see. Okay. Yeah, maybe just as a brief intro, so to say, I hope you all had a good day, a very inspiring one, as promised, so to say. I think you heard about all the nasty little gritty details that we've elaborated in the project. So thanks to all the partners, work package leaders, all the technical team for that. You also heard about the user perspectives, roadmaps, and last not least, you heard about the thing with the integration of the vehicle into the mobility system. And I think this is also, I think maybe the inspiration a little bit for what you get now for me, my final remarks, or call it conclusions. So I will turn myself into the background. You see my presentation. It will be a short one, and hopefully we can have some question and answers on the perspectives later on. So, yep, there you go. You've heard INFRAMIX in a nutshell today about what kind of solutions did we develop. Yep. We worked on the evaluation of all these nice little new things like traffic control strategies, new digital infrastructure elements, on microscopic, submicroscopic, real-world implementation. And also you heard about the hybrid simulation and real-world testing that we did. And last not least, of course, this led to recommendations on infrastructure classifications, on safety parameters, on developing a roadmap, but also on exploiting the different kind of technologies and solutions that we have done. So if we put it even more into what I call a nutshell, you see, it's what did we do? We did a focus on motorway scenarios. So we were not focusing, of course, on city traffic, rural areas, but I think there must be an alignment in the future. We have really shown that infrastructure or new means in infrastructures improve efficiency and safety in these kind of mixed traffic environments, as we call them, control strategies and so on. We tested new infrastructure elements, and we have defined the infrastructure support classes. As Tom pointed out just beforehand, yes, I think we have to be very careful. It's a theoretical concept, but I personally have the feeling it's a very helpful one. And last not least, we also did a perspective on the next 10 years ahead based on our learnings. So also this is very helpful. But because it's all about what I call the future role of infrastructure in the future. And of course, INFRAMIX is, as Tom also pointed out in this nice little graphic with all the projects, it's one of many infrastructure related projects dealing with what I call automation readiness. And we actually see key platforms, and of course, above all, the CCAM platform, to work on these future infrastructure perspectives: CEDAR, AirTruck, IRF, ASICAP, ITF. We even discussed this trilaterally with US and Japanese colleagues. And we defined the different kind of, let's say, topics: the physical and digital elements, the data quality, the scenarios we should look into at first, the cooperative driving and the communication infrastructures, the legal requirements. So how do we put it in the road code? And these more, what Tom also pointed out, important next, the systems approach, and also what does it has to do with new mobility services. But above all, it's clear infrastructure is a key question and domain for these future research initiatives, also pointed out in the, or for, so to say, the CCAM partnership in the future, in these, let's say, cluster number 4, as Tom mentioned it. And what do we see now as possible next step? Maybe also a little bit a conclusion from my side for the upcoming activities. Of course, we see more flexibility needed, and not only the specific focus on the first, let's say, scenarios, and of course, these linked to the ODDs with regard to road types, traffic volumes, different kind of scenarios. What elements do we need? What data do we need? How do we deal with redundancy, for instance? We need a wider perspective on the impacts on the evidence. It came out clearly that the first measures, or mainly the measures, go for efficiency and safety. But I think we all have to work on the co-benefits towards the environment, service orientation, maybe also towards resilience and robustness in the context of the COVID crisis. We have to combine also those measures that we were focusing in INFRAMIX with others to maximize the benefits of the infrastructure support. And of course, we have to look into the related costs and benefits, because I think this is really needed in the next steps. We have to integrate the legal framework, of course, because in the end, it's also about reliability, about quality, about trust in the infrastructure support. And we have to widen maybe the user perspective, so further feedback on the experience and how this guidance is working in reality and not only as a stated preference. And what's also in our perspective is quite important, collaboration. So from the infrastructure part, of course, with the OEMs, with the service providers, to exactly do these kind of integrating the vehicle into the infrastructure. And last not least, I would say, start implementing the no regret measures along this common vision and strategy. And I think it's because we also have to show things in practice and demonstrate things in practice. And maybe this is then also something where it's not only about the infrastructure in the end and what the road operators are doing, it's also promoting an I love infrastructure driving style in the future. This comes along with these infrastructure measures. So that's all. Thanks a lot for keeping, let's say, alive during the whole day with all the presentations. And I give back to Anna-Rita. Thank you.
Thank you, Martin. That was a very interesting presentation. That also leads us to more work to do in the future. So thank you, everybody, for joining us today. Here we are. I hope you found this webinar interesting and stimulating, and also maybe thought-inducing. So if you would like to get in contact with us, please do through our social media. There's also all the contacts that you need are in the handouts in the very first presentation that I gave this morning. Please be reminded that this session has been recorded, so it will be available for you on demand after this event. And also, I would like to repeat that all the presentations will be collected and then made available after the webinar conclusion in a follow-up email that you will receive in the next days. Again, thank you very much. It was a pleasure to have you and have such a lively time with you, with question and answers and experiences and results coming up. This is the end of this webinar, and I will now stop the recording. Thank you. Bye-bye. Have a good day ahead.